What if dinosaurs didn't actually go extinct? Not in the way we've always been told, not in the tidy story of a rock from space, a sky full of ash, and then silence. What if that story, as dramatic and as true as parts of it are, is only half the picture? What if something more mysterious, more layered, more alive has been unfolding beneath our feet and across our skies this whole time? Now, settle in. Let the weight of the day fall away from your shoulders. Let your breath slow down just a little, and come with me as we follow this question. Gently, curiously, like detectives in no particular hurry, all the way to where the evidence leads. Because here's the thing no one tells you in school. The story of the dinosaurs isn't over. It never was. It just changed shape. And that, if you ask me, is one of the most quietly astonishing things about the world we live in. Let's begin at the beginning, or at least the beginning most of us were handed as children. 66 million years ago, something fell from the sky. It wasn't small. Scientists estimate it was roughly 10 to 15 kilometers across, wider in fact than the depth of the Earth's crust in some places. A rock so large that if you stood at its edge and tried to see the other side, it would have vanished beneath the curve of the horizon. An object that, by any ordinary measure, should never have been able to survive its journey through space long enough to reach us. But it did. It entered the atmosphere moving at roughly 20 kilometers per second. 20 kilometers per second. Think about that for a moment, because it's almost too fast for the mind to properly hold. At that speed, the air itself couldn't get out of the way fast enough. The pressure that built up in front of the asteroid was so extreme that the rock was effectively travelling inside a bubble of superheated plasma, a ball of fire so hot it rivaled the surface of the sun. And when it finally struck what is now the Yucatan Peninsula of Mexico, in a region we call Chicxulub, it did not simply create a crater, it exploded. With the force of billions of nuclear weapons detonating simultaneously, in a single moment, a single irreversible moment. The initial impact vaporized everything within hundreds of kilometers. Rock, sea, soil, gone. Not burned, not melted. Vaporized. Turned into gas so quickly that the landscape simply ceased to exist. The shockwave moved outward at speeds no living thing could have outrun. Tsunamis 100 meters tall rolled across the Gulf of Mexico and far beyond, reshaping coastlines in hours. Earthquakes of a magnitude we have no frame of reference for rattled the entire planet. Geologists have found evidence of earthquake-triggered landslides on the far side of the world, triggered by that single impact. And then came the sky. The impact threw billions of tons of debris into the upper atmosphere. Not just dust, pulverized rock, vaporized sulfur from the limestone bedrock, carbon soot from the fires that erupted worldwide. This debris formed a thick, impenetrable shroud around the Earth, a veil that blocked sunlight. Now, here is where the story becomes not just catastrophic, but quietly tragic. Because the loss of sunlight is not an immediate death sentence. It's a slow one. It's a famine. Plants, which depend on sunlight to convert carbon dioxide into food, began to die. First they stopped growing, then they withered. And as they disappeared, every creature that depended on them for food began to starve. And every creature that depended on plant eaters for food began to starve as well. The cold set in. Temperatures dropped sharply. Some estimates suggest by as much as 15 or 20 degrees Celsius in certain regions. For creatures whose body temperatures were tied to their environment, this was simply unsurvivable. For larger animals, whose metabolisms required enormous amounts of food just to sustain basic body function, it was lethal. And the acid rain, when that sulfur reached the upper atmosphere and mingled with moisture, it came back down as sulfuric acid. It poisoned rivers, it poisoned soils, it killed even the surviving vegetation that had managed to endure the initial cold and darkness. It was, by every measure, the worst day in the history of complex life on Earth. And yet I find myself pausing here, every time I read about this, because there is a detail hiding inside the catastrophe. A small, stubborn, extraordinary detail that the dramatic version of this story tends to gloss over. Something survived. Not just survived. Survived, persisted, adapted, and in some cases went on to thrive. And that changes the whole shape of the story, doesn't it? Because extinction events, even mass extinction events, are never total erasures. They are filters. Harsh, terrible, arbitrary filters, but filters, not blank slates. The Chicxulub impact killed approximately 75% of all species on Earth. That number is staggering. Incomprehensible, really, when you sit with it. 3 out of every 4 species gone. Entire lineages that had endured for hundreds of millions of years simply deleted from the living world. But the other 25% remained, and among them, among the survivors, the scramblers, the lucky, the resourceful, the small and the hidden, were creatures whose stories are still unfolding today. Creatures whose ancestors walked the same ground as Tyrannosaurus rex. Creatures that carry in their very cells, in their very structure, the unmistakable signature of a lineage that stretches back far further than we can comfortably imagine. I'm going to let that sit for a moment, because it matters. It really matters, because when we ask the question, what if dinosaurs didn't go extinct, we tend to imagine something dramatic. We tend to picture a scenario in which the asteroid missed, or in which some population of massive thundering giants somehow held on in a remote corner of the world. And those versions of the story are interesting, we'll get to them. But the quieter, more remarkable answer, the one that science has actually been building toward for decades now, is something else entirely. Some dinosaurs didn't just survive, they're here right now. And you've probably seen one this week. We'll come back to that. First, though, let me take you somewhere more unexpected. Let me take you to the edges of the map, to the places where, even in our age of satellites and sonar and deep-sea cameras, the world still keeps secrets. Because the question of hidden survivors is older than the asteroid story. And it's stranger and more layered than you might think. When the first naturalists began cataloguing the world's creatures in the 18th and 19th centuries, they operated with a kind of optimistic certainty. The world was large, yes, vast and unmapped in many regions, but surely, they reasoned, anything significant, anything the size of, say, a large reptile, let alone a prehistoric giant, would have been documented by now. And yet, again. The world kept surprising them. Species kept turning up, not just small insects or obscure mollusks, large animals, consequential animals, animals that had been dismissed as legend, as myth, as the overactive imaginations of indigenous peoples and travellers who'd had too much sun. The okapi, first formally described by Western science in 1901, had long been reported by local Congolese people. The scientists had not believed them. The okapi, it turned out, was not only real but belonged to the giraffe family, a large, striking, unmistakable creature that had somehow remained undocumented by formal science well into the 20th century. The coelacanth, a fish that scientists had confidently declared extinct for 65 million years. A fish whose fossilized remains had been studied, catalogued, analysed. A fish that, in 1938, was pulled alive from the waters off the coast of South Africa by a local fisherman who had no idea what he had caught. When the naturalist Marjorie Courtenay-Latimer saw it in the fisherman's catch, she knew immediately that something was profoundly wrong with the confident story of prehistoric extinction. The fish was 4 feet long. It had fleshy, lobed fins that looked almost like limbs. It was ancient, it was unmistakable, and it was alive. The scientific community's reaction ranged from astonishment to embarrassment. How had this creature survived 65 million years undetected? How had the oceans kept this secret for so long? What else, the more honest scientists began to ask, might the world be keeping from us? It is a question that, if you sit with it long enough on a quiet night, becomes rather difficult to put down. Because the Earth is very large, and our ability to search it is, even now, far more limited than we generally like to admit. The ocean floor remains mostly unmapped. The deep jungles of the Congo Basin, the Amazon, the interior highlands of New Guinea, these are not regions where scientists routinely conduct exhaustive surveys. They are not regions where, if a large and cautious animal wanted to remain unseen, it would necessarily fail. We find new species every single year. Not just bacteria, not just insects. In 2008, the saola, a large forest bovine, was discovered in Vietnam, not described from a specimen. Described from the horns and skull of a creature that local hunters knew well and had never thought to mention to the visiting scientists, because it was simply part of their world. I find myself thinking about the saola when people say, with absolute confidence, that there couldn't be undiscovered large animals, that if something significant were out there, we would know about it, we would have found it, we keep being surprised. That's the honest truth. We keep being surprised. Now, none of this proves that prehistoric creatures are wandering the forests of Central Africa or the depths of unknown lakes. I want to be clear about that. The romantic image of living dinosaurs hiding in lost valleys is a beautiful fantasy, and I'm not going to pretend it's straightforward science. It isn't. But it isn't quite as easily dismissed as it once seemed either, and that distinction, that small, careful, intellectually honest space between proven and impossible, is where tonight's journey lives. So let's settle into that space. Let's be curious without being reckless. Let's follow the evidence and the questions and the mysteries and see where they lead. Because the real story, the one that science has been quietly assembling over the last few decades, is more astonishing than the fantasy. More astonishing because it's true. More astonishing because it means that every morning when you step outside, you are living in a world that still carries the living legacy of the Mesozoic era. The age of dinosaurs never really ended. It just changed. Before the impact comes, I want to take you there, to that world, to the late Cretaceous, approximately 68 million years ago. Because I think we do the dinosaurs a disservice when we treat them as mere set dressing for a catastrophe story. They deserve to be seen properly, to be understood in their context, in their world, in the full complexity of their lives before the last day came. Imagine the scene. You are standing on a floodplain in what will one day become the state of Montana. The air is warmer than the air of the modern American West, perhaps 10 degrees warmer, on average, because the planet is in a warm phase of its long climatic cycle. There is no ice at the poles, the seas are higher, and much of what is now the central United States lies beneath a shallow inland sea, the Western Interior Seaway, that stretches from the Gulf of Mexico to the Arctic Ocean, dividing the continent into two separate landmasses. The plants around you are, in some ways, recognizable. The Cretaceous saw the explosive radiation of flowering plants, the angiosperms, and by this late stage they have established themselves as the dominant vegetation across most of the world's landscapes. There are magnolias, willows and elms, early members of what will become the rose family. Grasses are beginning to appear, though they are still a minor component of the vegetation, and nothing like the great grasslands that will spread across the world in the Cenozoic. If you enjoy listening to sleepy prehistoric stories like this, subscribe. I post stories like this weekly. Alongside the flowering plants are the holdovers from earlier eras, ferns, still abundant and lush, filling the understory with their prehistoric fronds. Cycads, ancient and slow-growing, their palm-like forms casting shadows across the ground. Conifers, though reduced in dominance from the Jurassic, still present on the higher ground and in cooler regions. The smell of this world, and I find myself thinking about this more than almost anything else when I try to imagine the Mesozoic, would be extraordinary. The resin of conifers, the sweetness of early flowering plants in bloom, the mud and decay of river channels, the raw biological intensity of an ecosystem with millions of years of accumulated complexity, and the sounds. This is something we almost never discuss, but I find it endlessly fascinating. What did the Cretaceous sound like? We know that many insects were producing sound in the Cretaceous. Crickets and katydids, or their close ancestors, have left body plan evidence suggesting their sound-producing mechanisms were already in place. Cicadas were certainly present, and almost certainly as loud as they are today. The late Cretaceous would have had a constant insect soundtrack, much as tropical forests do today. We have strong evidence that theropod dinosaurs vocalized, not with the bellowing roars of the movies, because their syrinx, voice box, anatomy would have worked differently from mammals, but with closed-mouth sounds, booming, resonant, low-frequency calls similar in mechanism to the calls of modern emus and cassowaries, which produce infrasound by inflating throat pouches. These calls carry long distances, penetrating dense vegetation, communicating across the distances that large animals must navigate. Ceratopsians, the horned dinosaurs, almost certainly communicated visually, using their extraordinary head ornamentation for display. But they likely had vocal components too. Hadrosaurs, the duck-billed dinosaurs, had elaborate crests on their skulls that paleontologists have reconstructed as resonating chambers, essentially built-in instruments for producing distinctive calls. Different species would have had different calls, recognizable to their own kind, filling the late Cretaceous riverbanks with a diversity of sound that we can now only imagine. Now walk forward through this forest and pay attention. In the undergrowth, something moves. A small, fleet-footed creature, perhaps 40 centimetres long, feathered in patterns of brown and rust, moving through the low vegetation with the nervous intensity of a prey animal that knows it lives in a world of predators. This is a small dromaeosaur, a close relative of the famous velociraptor, though in the late Cretaceous of North America it would be a different species. It moves with the alertness of a hawk, head tilting from side to side, each eye scanning independently, looking for insects, for small lizards, for the eggs of other dinosaurs. Above it, in the branches of a magnolia, something else watches. A small bird, recognisably a bird, with flight feathers and a shortened tail, and a body plan that a modern ornithologist would immediately understand. The diversification of birds is already well underway in the late Cretaceous. Several lineages of modern birds, including the ancestors of modern ducks, shorebirds and possibly parrots, are present in late Cretaceous deposits. These are not transitional forms, these are birds, fully committed to the avian body plan, singing and flying and nesting in exactly the ways their modern descendants do. Move further through the forest, toward the riverbank. The sound of water, the specific quality of sound that a large, slow river makes, the gurgling over submerged obstacles, the lap against muddy banks, the rush through narrower channels. This river is broad and brown and full of life. Turtles bask on half-submerged logs. Crocodilians, by this point virtually indistinguishable from their modern equivalents, lie in the shallows, still as stone, their yellow eyes registering every movement on the bank, and then movement at the edge of your vision, movement on a different scale. Something is coming to the river to drink. You hear it before you see it. A deep, rhythmic impact, felt as much in your chest as heard with your ears, that announces weight. Real weight, the kind of weight that changes, the ground beneath it that produces its own small seismic signature. It steps from the tree line, and the scale of it requires a moment to absorb. An adult Edmontosaurus, one of the large hadrosaurs that dominated the late Cretaceous of North America, perhaps 8 meters long, perhaps 4 meters at the shoulder. A creature of extraordinary bulk, its body covered in skin that we now know, from exceptionally preserved specimens, was not the smooth reptilian hide of early reconstructions, but something subtler and more textured, bumped and scaled in complex patterns, perhaps with colour gradients we can only guess at. It moves with the unhurried confidence of an animal that knows, in its ancient nervous system, that it is large enough to be taken only by the largest predators. It walks to the water's edge, bends its neck, drinks, and behind it, emerging from the tree line in 2s and 3s, more Edmontosaurus, a herd of perhaps 20 adults with several juveniles moving among them. There is something deeply familiar about the dynamic, the same kind of mutual watchfulness you see in a herd of elephants, or a group of zebras at a watering hole. The animals at the periphery drinking more quickly, more nervously, while the larger central individuals take their time. The occasional communication, a low sound that carries, a head lift, a movement of ears. These are not alien beings. They are animals doing animal things, in a world that, for all its strangeness, operates on recognizable principles of ecology and behavior. And now, because the Cretaceous, like all ecosystems, includes its apex predators, pay attention to the tree line across the river. Something is watching the herd. You might not see it at first. The visual camouflage of large predators is often underestimated. They are not the bright, obvious presences of the movies. In the dappled shadow of the Cretaceous forest, a Tyrannosaurus rex is harder to see than you would expect, but the eyes of the hadrosaurs have been tracking it for several minutes, and the nervous energy of the herd has ratcheted up subtly. The peripheral animals drinking faster now, heads lifting more frequently. The Tyrannosaurus is approximately 12 meters long, approximately 6 meters at the hip, taller than a double-decker bus. Its body is covered, at this adult size, in a relatively sparse coat of filamentous integument, possibly retained from juvenility in certain patches, but mostly bare. The dark, weather-beaten skin of a very large ectotherm that spends significant time in the sun. Its forelimbs, those tiny vestigial arms that have inspired so many jokes, are pressed against its chest, serving their actual purpose as stabilizers for the massive torso during movement, and possibly for gripping prey. Its head is extraordinary, massive beyond any reasonable mammalian analogy. The skull alone is over 1 meter in length, the jaw capable of a bite force that exceeds that of any other known land. Predator, over 3 times the bite force of a large African lion, capable of crushing bone, capable of shearing through the frill of a ceratopsian, capable of inflicting injury that nothing short of another tyrannosaur could survive. And the eyes. Forward-facing, large, capable of stereoscopic vision more acute than a hawk's. Recent studies of T-Rex cranial anatomy have suggested visual acuity sufficient to detect movement at distances of 6 kilometers, more than 3 times the visual acuity of a modern eagle, which is already about 8 times as good as human vision. It is not the thundering, stupid monster of early Hollywood. Biomechanical studies of the legs, the thick bones, the enormous muscle attachment points, the ballistic evidence from preserved trackways suggest a top speed of perhaps 17 to 20 kilometers per hour. Not slow, but not a sprinter. Rather, an ambush predator with extraordinary sensory systems, hunting through stealth and patience in the forest, edge, using the cover of vegetation to approach much closer than its size would suggest before committing to an attack. The herd has noticed it now. The energy shifts completely. The animals at the water's edge back away. The juveniles are herded toward the center of the group. There is a moment of extraordinary tension, 2 of the larger adults turning to face the predator's direction, their crests flushing with color in what may be a threat display or a communication to the predator itself. And then, nothing. The Tyrannosaurus turns away. It moves back into the tree line. This was a reconnaissance, a testing of the herd's cohesion, a gathering of information. The predator will not be hunting today, not with a vigilant, healthy adult herd in good condition. It will wait. It has time. It has always had time. The herd relaxes, returns to the water. The afternoon light shifts through the Cretaceous canopy, and in the branches of the magnolia the small bird that has been watching all of this begins to sing. This is the world that was. This is what was lost on the day the sky changed. And this is what, in that altered and impoverished and surviving form, persists. The bird is still here, still singing. The world changed enormously, but it did not start over. It carried forward, diminished and transformed, but carrying, in every cell of every surviving creature, the inheritance of the world that had been. When I think about that, when I really let myself feel the weight of that continuity, I find something that is, strangely, almost comforting, not in spite of the catastrophe, but through it. Life found a way, as it has always found a way, as it will presumably always find a way, long after our own brief chapter has come and gone. The late Cretaceous is 66 million years away, and it is also outside your window every morning in the voice of every bird that sings in the light. There is a particular kind of discovery that doesn't announce itself with fanfare. It doesn't arrive in a blaze of revelation with newspaper headlines and scientific celebrations. Instead, it creeps in quietly, over decades, accumulating piece by piece, until one day you look up and realize that the entire framework of your understanding has been gently, irreversibly transformed. The discovery that birds are dinosaurs is exactly that kind of discovery, and I want to spend some time here because I think most people, even people who've heard this fact before, who've nodded along when someone mentioned it, don't quite let it in, don't quite let themselves sit with what it actually means. So let's do that. Let's really sit with it. In 1861, just 2 years after Charles Darwin published On the Origin of Species, a limestone quarry in Bavaria, Germany, produced one of the most extraordinary fossil finds in scientific history. Workers splitting stone encountered the unmistakable impression of feathers preserved in ancient rock. And when more of the specimen was excavated, what emerged was a creature that seemed impossibly caught between worlds. Archaeopteryx, ancient wing. It had feathers, beautifully preserved, clearly feathers, but it also had teeth, a long, bony tail, clawed fingers at the end of its wings, the skeleton of a small theropod dinosaur, unmistakably wearing the feathers of a bird. Darwin himself was delighted. Here was transitional evidence of exactly the kind his critics had demanded. Here was a creature sitting precisely at the boundary between 2 groups that had, until that moment, been thought to be entirely separate. But the full implications of Archaeopteryx took a long time to metabolize. Scientists spent the better part of a century debating exactly what it was, where it fit, whether birds really were dinosaur descendants or merely dinosaur relatives. The picture was complicated, The evidence fragmentary, the arguments fierce. And then, beginning in the 1990s, in a series of limestone formations in northeastern China, the ground shifted permanently. China's Yixian and Jiufatang formations, laid down roughly 125 to 130 million years ago, began yielding fossils unlike any seen before. Not just Archaeopteryx-type creatures, an entire ecosystem of feathered dinosaurs. Species after species after species, each with feathers in different configurations serving different apparent purposes. Some were clearly capable of flight, others were ground dwellers, with feathers that must have served other functions: display, insulation, brooding warmth over eggs. Sinosauropteryx was among the first, a small Compsognathus-like dinosaur with unmistakable filamentous feathers covering its body. Not flight feathers, just feathers. Insulating, colourful, present. Microraptor followed, a four-winged glider whose hind limbs bore flight feathers as well as its forelimbs, a configuration that had no living parallel but made extraordinary sense as an intermediate stage in the evolution of powered flight. Caudipteryx, Protarchaeopteryx, Yuanchuaves, Yisi with its bizarre bat-like membrane wings supported by an elongated wristbone found in no other known creature. Each one adding another piece to a picture that was becoming, with every passing excavation season, both more complex and more coherent. The picture showed that feathers were not a bird invention. Feathers were a dinosaur invention. Specifically, they were a coelurosaur invention, arising within the group of theropod dinosaurs that includes the tyrannosaurs, the dromaeosaurs, the ornithomimesaurs, and eventually the birds. And here's where I have to pause and ask you to sit with something genuinely strange. Tyrannosaurs had feathers, not all of them, not the full-grown adult Tyrannosaurus rex. Evidence suggests that at its enormous adult size, feathers may have been largely shed or reduced, as has been proposed for modern elephants, whose ancestors were once furrier. But juvenile tyrannosaurs, and many of the smaller relatives of T, rex, animals like Eutyrannus, Dilong and others, were feathered, covered in a coat of filamentous proto-feathers that would have given them an appearance quite unlike the scaly, leathery monsters of the movies. This changes things, doesn't it? In a quiet but profound way. The dinosaurs were not quite what we imagined. They were not entirely the reptilian, cold-blooded, plodding giants of the early 20th century reconstructions. At least some of them, perhaps many of them, were warm-blooded or near-warm-blooded, fast-growing, potentially highly intelligent by the standards of their era. And at least some of them were covered in feathers, which means that when you look at a modern bird, really look at one, really let yourself see it. You're not looking at a creature that descended from something like a dinosaur. You're looking at a dinosaur. A living, flying, singing, nest-building dinosaur. The line from Velociraptor to a modern hawk is not a line of descent from one group to another. It is a continuous thread of inheritance within a single lineage, the same evolutionary family tree. The hawk is more closely related to Velociraptor than Velociraptor was to Triceratops. Let me say that again, because it's worth holding. A modern bird is more closely related to Velociraptor than Velociraptor was to Triceratops. The distance between a sparrow and a raptor, evolutionarily speaking, is shorter than the distance between two creatures we comfortably call dinosaurs. And so, the birds. There are approximately 10,000 known species of birds alive today. 10,000. Compare that to the perhaps 3,000 species of non-avian dinosaurs that have been identified in the fossil record, and you begin to see that the extinction of the dinosaurs was, at most, a partial one. A dramatic pruning of the family tree. A catastrophic culling of all the branches that didn't lead to birds, but not an ending, not a true ending. The birds that survived the Chicxulub impact did so partly through luck, being in the right place, the right size, with the right dietary flexibility to endure the catastrophe. But they also survived because they possessed a suite of characteristics that served them well in a broken, impoverished world. Small body size meant lower caloric requirements. The ability to eat seeds, which, unlike leaves and fruit, could survive in the soil for extended periods even after the plants that produced them were dead, provided a food source that many other creatures couldn't access. And the capacity for flight gave access to resources and refuges that ground-bound creatures couldn't reach, and so they endured. Scraggly, reduced in diversity but enduring. And in the 10 million years that followed the impact, a period called the Paleogene, the surviving bird lineages diversified explosively into ecological niches left vacant by the mass extinction. into forms and sizes and lifestyles that we would barely recognize as bird-like. Some grew enormous. Gastornis, sometimes called diatryma, was a flightless bird that stood nearly 2 meters tall and possessed a skull and beak so massive that, for many years, scientists assumed it was a predator, an apex predator, a bird playing the ecological role that the tyrannosaurs had vacated. Later analysis of its bone chemistry suggested a more herbivorous diet, but the picture of a giant flightless bird dominating the Paleogene landscape of North America and Europe is arresting regardless. And then there was Phorus racidae, the terror birds, a South American lineage of flightless predators that persisted for tens of millions of years, running down prey on the open plains with long legs and dispatching it with hooked beaks capable of cracking bone. The largest of them, Kelenken guillemois, stood nearly 3 meters tall. It had a skull over 70 centimeters long, bigger than a horse's head. Terror birds were not some marginal, short-lived evolutionary experiment. They were the dominant large predators of South America for roughly 60 million years. 60 million years! That is a span of time so long that, from the terror bird's perspective, we ourselves are barely a brief interruption. They only went extinct when the Isthmus of Panama formed, connecting North and South America and allowing large North American predators, felids, canids, large bears, to migrate south and outcompete them. The last terror birds disappeared roughly 2 million years ago. But here's the thing. Even that extinction didn't end the bird story as predators. Hawks, eagles, and owls today occupy the same ecological role that the terror birds once played. Birds of prey remain among the apex predators of many ecosystems, controlling rodent and small mammal populations, filling the same conceptual niche that their non-avian ancestors occupied for hundreds of millions of years. And then there's the cassowary. If you've never really thought about a cassowary, I encourage you to do so. Because the cassowary, standing in the rainforests of northern Australia and New Guinea, is one of the most compelling arguments for the idea that the age of dinosaurs never truly ended. It stands over 1.5 meters tall. It carries a prominent bony casque on its head, a structure whose function is still debated but which may serve as a display feature, a weapon, or an amplifier for low-frequency sound. Its legs are extraordinarily powerful, ending in clawed feet with a dagger-like inner toe that can grow to over 12 centimeters in length, and has been documented inflicting severe injuries on humans and predators alike. It cannot fly. It has reduced wings that end in sharp, spiny quills. It communicates through low-frequency booming calls that can travel through dense forest. It is deeply territorial, fiercely protective of its offspring. In cassowaries, the males incubate the eggs and raise the chicks alone, and possessed of a level of wariness and intelligence that makes it remarkably difficult to study in the wild. When you look at a cassowary, you're not looking at something that feels like what popular culture calls a bird. You're looking at something that feels, in its posture, its movement, its presence, its threat, like a dinosaur. Not metaphorically, literally. And it is. It is a dinosaur. A living, breathing, striding, dangerous dinosaur in the forests of our contemporary world. The same is true, in less dramatic form, of every bird you've ever seen. The starling at your window, the crow on the fence, the tiny wren singing from the hedge in the early morning, filling the air with a song that is, if you think about it, the same kind of territorial vocal display that dinosaurs must have made in the Mesozoic forests, communicating, claiming, connecting. I find, when I let myself really hold this thought, that the world becomes both stranger and more beautiful, because we've been living alongside dinosaurs our entire lives, every morning when the birds begin singing before the sun comes up. The world is briefly filled with the descendants of creatures that survived an extinction event that killed most of life on Earth. Every time a hawk circles overhead, you are watching the direct evolutionary continuation of the lineage that produced Velociraptor. The dinosaurs are not gone, they never were. They just grew wings and learned to sing. And in the early morning, when the light is soft and the garden is still and the birds are just beginning, I think that's worth a moment of genuine quiet wonder. Now let's explore a different kind of survival. Not transformation, not the dramatic reinvention of dinosaurs into birds, but the even stranger story of creatures so perfectly adapted to their environments that they simply didn't need to change very much at all. creatures that arrived at a working solution to the problem of existence so early, so completely, that the intervening millions of years have left them largely as they were. We call them living fossils. The term was coined actually by Charles Darwin himself, a scientist who, more than most, understood the enormous pressure that time and change exert on living things. When Darwin used it, he meant creatures whose bodies closely resemble their ancient ancestors. Creatures that appear, when placed beside their fossilized predecessors, almost unchanged. The coelacanth is the most dramatic of these, and we've already mentioned it. But it is far from alone. Consider the horseshoe crab. Not a crab at all, despite its name, but an arthropod more closely related to spiders and scorpions. The horseshoe crab has been on Earth for roughly 450 million years, older than the dinosaurs by nearly 200 million years, older than any land-walking vertebrate, older than the first forests. It survived the Permian extinction, which killed 96% of marine species. It survived the Triassic extinction. It survived the Chicxulub impact. It survived everything. And it is largely unchanged. A horseshoe crab today would have been recognizable, identical, essentially, to one of its ancestors from the Ordovician period. Its biology, its behavior, its fundamental design, all preserved with remarkable fidelity across nearly 500 million years. I find the horseshoe crab deeply reassuring, in a way that's hard to explain. It says something about the resilience of successful designs, something about the way life, once it finds a solution that works, can be extraordinarily reluctant to abandon it. Now. The most relevant living fossils for our purposes tonight are, of course, the reptiles. Because while the non-avian dinosaurs were overwhelmingly killed by the Chicxulub impact and its aftermath, they were not the only reptilian lineage that faced that catastrophe. They were accompanied by cousins, by relatives, by evolutionary neighbours, and some of those neighbours made it through. The crocodilians, the turtles, the tuatara. Let's begin with the crocodilians, because they are the most direct, the most obvious, the most in-your-face evidence of Mesozoic survival. Crocodilians, the family that includes modern crocodiles, alligators, gharials, and caimans, are not technically dinosaurs. They branched off from the same ancestral lineage, the archosaurs, at the beginning of the Triassic period, roughly 250 million years ago. Dinosaurs went one way, crocodilians went another. But they are the closest living relatives of dinosaurs among non-avian animals. Crocodilians and birds are together the only surviving members of the archosaur lineage. And crocodilians have been on Earth, in essentially recognizable form, for roughly 95 million years. Specimens from the Cretaceous period, the last age of the dinosaurs, look remarkably familiar. You would know them for what they were, and they survived. While the non-avian dinosaurs perished, the crocodilians endured the impact winter, the acid rain, the disruption of the food, chains, the cold. How? Several reasons. Crocodilians are ectothermic. Their metabolism is regulated by external temperature rather than maintained internally. This means they can slow their metabolism to near zero during cold periods. An adult crocodile can go months, even years, without eating if necessary, drawing on fat reserves and entering a state of torpor that essentially pauses its biological clock. Their digestive systems are extraordinarily efficient, capable of extracting nutrition from materials that would defeat most other vertebrate digestive systems. They can eat carrion that would be toxic to mammals. They can eat bone. They can survive on prey items that are sporadic and unpredictable. They can hold their breath for extraordinary lengths of time, up to 2 hours in some species, allowing them to shelter in underwater refuges during surface-level catastrophes. They excavate burrows. They are in every sense built for endurance. And endure they did. When I watch a crocodile lying in the sun beside an African river, and I've been lucky enough to do exactly that, to sit on a riverbank and watch a Nile crocodile with its ancient yellow eyes, half closed in the afternoon light, I am aware that I am watching an animal that existed before the first flowering plants bloomed, before the last great mountain ranges were raised, before the continents completed their slow drift into the shapes we recognize today. There is a stillness to crocodilians that isn't just physical, it's temporal. They have a quality of deep time about them. They do not seem to be in a hurry. Why would they be? They have outlasted everything. The turtles are even older, and their survival story is equally remarkable. Turtles and tortoises represent one of the most ancient vertebrate body plans still in active use. The turtle shell, that extraordinary modification of the ribcage and spine into a protective dome, first appeared roughly 220 million years ago in the Triassic period, and it was so successful, so effective as a defensive strategy, that evolution has largely left it alone since. Turtles survived the Chicxulub impact. They survived the transition from the Mesozoic to the Cenozoic era. They are still here. And while some lineages, particularly the larger sea turtles and the enormous freshwater turtles of the Mesozoic, did not survive, the basic turtle plan has persisted without fundamental modification for over 200 million years. I think about turtles differently since I learned how old they are. The leatherback sea turtle, which can grow to over 2 meters in length and weigh nearly 1,000 kilograms, has ancestors that were swimming the same ocean when the first dinosaurs were just beginning to establish their dominance on land. When Tyrannosaurus rex was alive, there were sea turtles. When the asteroid hit, sea turtles were swimming through the devastated oceans. And today, sea turtles are still swimming, tracking the same magnetic fields, laying eggs on the same general coastlines, following routes through the ocean that were established before humans existed, before our primate ancestors existed, before mammals in general were more than small, nocturnal insectivores hiding from the dinosaurs. And the tuatara is possibly the most astonishing living fossil we know of. It lives only in New Zealand, specifically on small offshore islands where predators introduced by humans have not reached, and from the outside it looks like a large, heavily built lizard, maybe 30 centimeters long, covered in grey-green scales, with a crest of spines running down its back. But the tuatara is not a lizard. It is not closely related to lizards. It belongs to a lineage, the Rhynchocephalia, that separated from the ancestors of modern lizards and snakes roughly 240 million years ago. Every other member of that lineage is extinct. Every fossil relative we have found, every evolutionary neighbour, all gone. Only the tuatara persists. Its biology is extraordinary. It grows extraordinarily slowly, reaching sexual maturity in 10 to 20 years. It lives for over 100 years in some cases, possibly much longer. Its metabolism is among the lowest recorded for any reptile. It can be active at temperatures as low as 7 degrees Celsius, where most other reptiles would be immobile. It has a third eye, a primitive photosensitive organ on the top of its head that degenerates, and is covered by scales in adulthood, but is functional in juveniles, and is thought to help calibrate the animal's circadian rhythms. A third eye, sitting quietly on top of the skull, seeing in some diminished way, tracking the light. When scientists first examined the tuatara's teeth, they found something that had no parallel in living reptiles. Teeth fused directly to the jawbone, worn down in a distinctive way that matched perfectly with teeth found in rhynchocephalian fossils from the Triassic and Jurassic periods. Its teeth are structurally, functionally, morphologically identical to those of its ancestors from over 150 million years ago. The tuatara has been on Earth, in more or less its current form, longer than most mountain ranges, longer than the Atlantic Ocean, which began opening only about 180 million years ago, longer substantially than the entire lineage of flowering plants. I find the tuatara almost impossible to fully comprehend. When I look at photographs of it, and photographs are all most of us can access since it's carefully protected and its island homes are generally restricted to researchers, I see something that looks, on the surface, almost ordinary, a sturdy grey lizard-like creature, and then the numbers begin to fall into place. 240 million years, the same lineage, unchanged, and I am simply, quietly astonished. These creatures, the crocodilians, the turtles, the tuatara, are not metaphors for survival. They are survival. They are living demonstrations of the extraordinary persistence of life, of the deep conservatism that occasionally asserts itself in evolutionary history, of the strange fact that sometimes the most ancient solution is still the best one. They share the world with us. They've always shared the world with us. They were there before us, and if we give them half a chance, they'll be there after us. There is something humbling about that, something that puts our brief, busy, noisy species in perspective. We are newcomers in a very old house, surrounded by roommates who arrived long before us and who, with appropriate care and restraint on our part, will outlast us too. That thought, I find, is not a sad one. On the contrary, it makes the world feel larger, deeper, more layered with time, more mysterious, more worth paying attention to, A kind reminder to not forget to subscribe to keep the channel alive. Let's take that sense of mystery and stretch it even further, because so far we've been talking about creatures that science has documented, measured, confirmed. We've been on firm ground, well, on ground as firm as anything 66 million years old can be, but there is another conversation to be had, one that lives in a different register, one that science approaches more cautiously, and which deserves exactly that caution, but which also deserves, I think, a fair and curious hearing. Because humans have been telling stories about surviving prehistoric creatures for a very long time. Not just the academic stories, the folk stories, the encounter stories, the ones passed down through generations in regions far from Western scientific institutions, told matter-of-factly by people who were simply reporting what they had seen. And some of those stories are very difficult to completely explain away. There is a particular kind of story that scientists find professionally uncomfortable, not because it's clearly false, not because the people telling it are unreliable, but because it doesn't fit neatly into the categories science has established. It sits at the edge of things, neither confirmed nor dismissed, neither fully explained nor fully unexplained. These are the stories we're going to explore now. I want to be clear about my own position on them. I am not going to tell you that these stories are proof of surviving prehistoric creatures. I am not going to ask you to suspend your critical thinking. What I am going to do is treat these accounts with the same respectful, curious attention I'd give to any other kind of evidence, and I'm going to let the strangeness of some of them speak for itself. The Congo Basin. It covers approximately 3.4 million square kilometers. It is the world's second largest tropical rainforest after the Amazon. Large portions of it remain poorly surveyed even today, not because they're inaccessible in principle, but because they're difficult, expensive, and often politically complicated to access. The region harbours extraordinary biodiversity, including species that have been formally discovered within living memory, and for well over a century reports have emerged from the indigenous people of certain regions, particularly from around Lake Tele in the Republic of Congo, of a large animal that does not match any known species, the Mokelembembe. The name translates roughly as one who stops the flow of rivers in the Lingala language. Descriptions vary somewhat, as you'd expect from a creature reported across a large region by many different people over many generations. But certain elements are consistent. The animal is described as very large. Estimates range from 5 to 15 meters in length. It is semi-aquatic, spending time both in and around deep river systems and lakes. It has a long neck, a relatively small head, a rounded large body and a long tail. Western scientists began collecting these reports systematically in the 19th century. The first formal documentation appears in a 1909 report by Lieutenant Paul Gratz, a German colonial officer who recorded accounts from local people along the Camelondo River. Subsequent expeditions, there have been many, by researchers from Europe, North America and Japan, collected additional testimonies and in a small number of cases reported their own anomalous observations. What should we make of this? The skeptical case is strong. No physical evidence has been retrieved. No body, no bone, no photograph that withstands scrutiny, no clear footage. Every large-scale expedition has returned without confirmation, and paleontologists point out the formidable difficulties of a large semi-aquatic animal going undetected in an era of aerial survey, satellite imaging, and camera trap technology. But the sympathetic case is also worth considering. The Congo Basin is genuinely difficult terrain. Camera traps placed without extensive local knowledge can cover the same small areas repeatedly, while vast regions go unsurveyed. The okapi was formerly undescribed until 1901 despite being well known to local people. The forest elephant was treated by many Western scientists as a population variant of the savanna elephant until 2001, when genetic analysis confirmed it as a fully separate species. The bonobos, our closest relatives alongside chimpanzees, were not formally distinguished from common chimpanzees until 1929. The Congo keeps secrets. That is simply, factually true. I'm not telling you the Mokelembembe is a surviving sauropod dinosaur. The honest scientific position is that we don't know what it is, if it exists as a distinct animal at all. Some researchers have suggested it might be a large monitor lizard or a misidentified forest elephant. Others suggest the descriptions themselves, transmitted across generations and interpreted through a Western scientific lens, may have accumulated distortions that make the original animal, whatever it was, unrecognizable in the accounts. But I find it interesting. I find the consistency of certain descriptive elements interesting. I find the longevity of the accounts interesting. And I find it interesting that experienced naturalists who have spent time in the region, people with professional reputations at stake, have occasionally returned speaking carefully, hesitantly, about something they couldn't quite account for. There is a similar story from Papua New Guinea. In the interior highlands and coastal regions, indigenous people have long reported a creature they call ropens, or in some areas, dua. The descriptions are of a large flying animal, described as having a wingspan of several meters, a long pointed crest on its head, a long tail ending in a diamond-shaped flange and bioluminescence, a visible glow, particularly at night. The crest, the tail flange, the large size. The descriptions, when written down and placed alongside pterosaur reconstructions from the Cretaceous period, draw immediate comparisons to pterodactyls, specifically to large pterosaurs of the Pterodactyloidea group. Again, I am not telling you that pterosaurs are alive in Papua New Guinea. The scientific consensus is very clear that pterosaurs perished in the Chicxulub event, along with the non-avian dinosaurs, and the obvious challenges of a large flying vertebrate going undetected, even in remote highland terrain, are significant. But indigenous peoples of Papua New Guinea are not a monolithic group, and the accounts come from multiple linguistically and culturally distinct communities across different time periods. The consistency of specific morphological details, the crest, the tail flange, the glow, across communities that may never have had contact with each other is something that asks for an explanation, even if that explanation turns out to be nothing more than the intriguing question of why these separate communities would converge on such similar descriptions. Bioluminescence, incidentally, is more widespread in the animal kingdom than was appreciated even 50 years ago. Deep-sea fish, certain fungi, fireflies and their relatives, some sharks. The list of bioluminescent organisms is long and still growing. The idea of a large flying animal with some capacity for bioluminescent display is not, from a purely biological standpoint, inherently absurd. Whether it describes a real contemporary animal is a different question. Let's move to the oceans, because the ocean has its own cryptozoological mystery, and one that is, if anything, better documented than the Congo Basin or Papua New Guinea reports. The sea serpent. Accounts of enormous elongated sea creatures date back to ancient Norse records, to the journals of medieval mariners, to the logs of naval officers and merchant captains across centuries and cultures. Most of these can be explained. Some, genuinely some, cannot be, even now. The most interesting piece of physical evidence is a category of encounter that recurs specifically in the 19th and 20th centuries, the carcass. Large, decomposing bodies, washed ashore or hauled up in fishing nets that don't match any known species. The most famous of these is the Zuyo Maru carcass. In April 1977, a Japanese trawler fishing in the Pacific Ocean off the coast of New Zealand hauled up in its nets a decomposing body of considerable size. The crew photographed it extensively before releasing it. It was too large and too foul-smelling to bring aboard. The photographs show a creature approximately 10 meters long, with a small head on a long neck, 4 paddle-like fins and a tapering tail. The carcass smelled strongly of decomposition, but showed no signs of the ammonia odor characteristic of sharks. When the photographs reached Japan, they created a sensation. The images were placed on a commemorative stamp. Scientists from several institutions analysed the photographs intensively. Their conclusions have remained frustratingly divided ever since. The majority view is that the carcass was a decomposed basking shark. When sharks decompose, they can lose their distinctive features in ways that leave an elongated, small-headed shape that superficially resembles the classic sea serpent silhouette. The shark hypothesis is plausible. It is the scientific consensus. But a significant minority of researchers, including some with genuine expertise in marine vertebrate anatomy, have argued that certain features in the photographs, the nature of the fins, the skeletal elements glimpsed in some shots, the body proportions, do not match a decomposing basking shark as cleanly as the consensus suggests, that the case is somewhat more open than it is generally presented as being. And then there is the nitrogen content. A sample of material was taken from the body before it was released. Chemical analysis later found the protein components to be inconsistent with shark tissue, which proves nothing definitively: sample contamination, misidentification of the tissue type, the complications of advanced decomposition, but adds another small wrinkle to a story that has more small wrinkles than is commonly acknowledged. I am drawn to these stories not because I believe in sea monsters in any sensational way. I'm drawn to them because the ocean is three-dimensional, vast and mostly unexplored. We have mapped more of the moon's surface than we have mapped the ocean floor. The deep sea continues to yield new species with regularity, including very large ones. In 2004, the first live footage of a giant squid was captured in the deep Pacific. Giant squid reach lengths of 12 to 13 meters. They have eyes the size of dinner plates. They were described for centuries by sailors and fishermen and dismissed as myth. They are not myth. The ocean clearly still contains surprises. What those surprises are and whether any of them represent survivors from deeper geological time remains genuinely open. And I find in that openness, in that honest acknowledgement that the map still has blank spaces, that the deep places still hold their counsel, something that feels like wonder. Like the world is larger than our current inventory of it. Like the mystery is not a problem to be solved and filed away, but a quality of the world itself. An indication that we are still, always, at the beginning of understanding. That seems right to me. That feels somehow appropriate. A world with no remaining mysteries would be a lonelier world than the one we actually live in. AC6. The road not taken. What if the asteroid had missed? Now let's step into a different kind of speculation. The kind that paleontologists and evolutionary biologists sometimes engage in, not as science fiction, but as a way of illuminating what we know about evolution and ecological dynamics by asking what might have been. What if the asteroid had missed? It is not as far-fetched a premise as it might sound. The Chicxulub impactor arrived at a particular angle, roughly 60 degrees, that maximised the distribution of sulfur aerosols into the upper atmosphere. Had it arrived at a shallower or steeper angle, the environmental consequences would have been substantially less severe. Had it struck an ocean basin rather than sulfur-rich carbonate rock, the sulfur release would have been much lower. Had it been even a few kilometres smaller, the energy released would have been insufficient to trigger a global winter of the magnitude that killed the non-avian dinosaurs. The near-miss quality of the Chicxulub event is something scientists have noted with what amounts to existential discomfort. The conditions that made it a mass extinction event rather than a very large regional catastrophe were specific and, in retrospect, almost implausibly well calibrated. A slight change in almost any of the key variables would have resulted in a different outcome, and a different outcome would mean a very different world. So let us imagine it. Let us imagine gently a world in which the late Cretaceous ecosystems were disrupted but not destroyed, a world in which the non-avian dinosaurs survived. What would that world look like? The first thing to understand is that dinosaur is not a category that describes a particular body plan or lifestyle. It describes an enormously diverse group of animals that occupied almost every ecological niche available to large terrestrial vertebrates. Dinosaurs were browsers and grazers, predators and prey. Some were fast, some were slow, some were large, some were tiny, some were solitary, some, the evidence increasingly suggests, were highly social. Some, we now know, were feathered and possibly colourful. Some may have been capable of surprising behavioural complexity. In a world where this diversity persisted, evolution would have continued. 66 million more years of selection, adaptation, speciation. The titanosaurs, the massive sauropods that dominated the late Cretaceous, would likely have continued their evolutionary trajectory toward gigantism in some lineages and miniaturization in others. We already see this pattern in the fossil record. Island populations of sauropods evolved into dwarf forms, while mainland populations trended toward the enormous. With 66 million more years of this dynamic, the sauropod lineages might have produced forms even more varied than those we know from the fossil record. But here is where it gets interesting, and where the science becomes genuinely provocative. The late Cretaceous was already showing signs of change. Mammal lineages were diversifying. Flowering plants had taken over many terrestrial ecosystems in a relatively short time. The climate was shifting. Some paleontologists have argued that the non-avian dinosaurs were, in certain lineages, already beginning to decline, that the Chicxulub impact hit a world of dinosaurs that was already, in some ways, under ecological stress. Others disagree, pointing to flourishing dinosaur diversity right up to the end of the Cretaceous record. The debate continues. But let's assume, for the purposes of our thought experiment, that the dinosaurs were healthy and diverse. What would 66 million years of continued evolution have produced? One of the most intriguing lines of speculation concerns intelligence. The dinosaurs that were, in the late Cretaceous, the most encephalized, the ones with the largest brain-to-body size ratios, were precisely the small theropod dinosaurs, the coelurosaurs, the Troodon, the Deinonychus relatives, the ancestors of birds. Troodontids, a family of small theropods closely related to birds, had encephalization quotients higher than most living reptiles, not as high as mammals, not as high as birds like ravens and parrots, but considerably higher than, say, a crocodile or a Komodo dragon. And in the 1980s, the paleontologist Dale Russell explored, in a now famous paper, what might have happened if Troodon-like dinosaurs had continued evolving along the same trajectory of increasing encephalization for another 66 million years. The result, speculative, hypothetical, deliberately provocative, was the Dinosauroid, a bipedal, large-brained, manipulative-limbed creature that Russell and his collaborator, artist Ron Segan, reconstructed as looking surprisingly, some would say uncomfortably humanoid. The Dinosauroid has been criticized heavily by other paleontologists. The assumption that increasing intelligence would necessarily produce a humanoid body plan is almost certainly wrong. Convergent evolution operates under constraints and opportunities that vary enormously between lineages, and there's no particular reason that a highly intelligent dinosaur would look like a reptilian human. More likely, a highly encephalized theropod would retain much of its theropod body plan while expanding and reorganizing its neural capacity in ways specific to its own evolutionary history. But the underlying question is legitimate and interesting. Would 66 million more years of dinosaurian evolution have produced any lineage of genuinely high intelligence? Any lineage of tool users? Any lineage capable of anything we might cautiously call culture? We cannot know. And I think the honest answer is that we cannot even confidently say whether it would or wouldn't have happened. Intelligence has evolved multiple times on Earth, in birds, in mammals, in certain fish and invertebrates, which suggests it's not an evolutionary fluke. But it also hasn't been universal, and most lineages with tens of millions of years of available time have not produced it. The emergence of intelligence may require specific ecological circumstances, particular pressures and opportunities that can't be predicted simply from brain-size trends. What we can say is that the non-avian dinosaurs, given enough time and the right conditions, represented a biological substrate rich enough, varied enough, and in some cases already trending toward enough neural complexity that high intelligence was not out of the question. Whether it would have arrived in time, whether 66 million years later we would be sharing a planet with a bipedal large-brained descendant of Troodon, nobody can say. But here's the flip side of that thought experiment, the one that makes it genuinely interesting rather than simply imaginative. If the non-avian dinosaurs had survived and continued to evolve, if the large theropods, the sauropods, the horned ceratopsids, the armored ankylosaurs had all persisted, what would have happened to the mammals? The honest answer is, probably not much. In the late Cretaceous, mammals were, with a few exceptions, small. Many were nocturnal. They occupied a limited range of ecological niches, largely insectivore and small omnivore roles, precisely because the dinosaurs had locked up most of the other options. The mammalian lineage had been present for over 100 million years before the Chicxulub impact, and in there, all that time, had not produced anything larger than a domestic cat in most lineages. In a world where the dinosaurs survived, mammals would almost certainly have remained small, marginal, and limited. The evolutionary radiation that produced elephants, whales, horses, lions, primates, all of it, happened only because the mass extinction opened up a vast array of ecological opportunity. In a world where that opportunity never opened, the mammals might still be hiding in the undergrowth, eating insects in the dark, which means that in a world where dinosaurs didn't go extinct, there is very likely no us, no hominids, no primates of the current kind. The particular evolutionary trajectory that led through early placental mammals to apes to our genus is a trajectory made possible only by the catastrophic vacancy of the post-impact world. We owe our existence to the asteroid. That is a profoundly strange thing to contemplate, that the most catastrophic event in the history of complex life, on Earth the event that killed roughly 3/4 of all species, was also, indirectly, the event that made us possible. That the very worst thing that happened to the Mesozoic world was the best thing that could have happened for the eventual emergence of beings capable of thinking about it. I don't know whether to find that comforting or disturbing, maybe both, The universe is, in this as in many things, indifferent to our preferences, but it is interesting, genuinely, deeply interesting. The kind of interesting that, if you let it, keeps you awake at night in the best possible way, not with anxiety, but with the peculiar exhilarating buzz of a mystery that you can think around the edges of but never quite fully grasp. The road not taken, the dinosaur civilization that wasn't, the mammals that would have remained small and frightened in the shadows if not for a rock from space. These are the thoughts that make deep time feel less like a museum and more like a living story. A day story still unfolding, a story of which we are merely the most recent, and most certainly not the final chapter. There is a question that has been hovering at the edge of this conversation since we began, and it would feel like a genuine omission not to address it. Can we bring them back? Not metaphorically, not through the discovery of living survivors, but through the most direct and audacious method imaginable, using genetics to recreate animals that no longer exist. The question gained cultural traction with the publication of Michael Crichton's novel Jurassic Park in 1990, and the Spielberg film that followed in 1993. Crichton's premise was elegant: dinosaur blood, preserved in the gut of mosquitoes trapped in amber, could be extracted, and the DNA recovered from that blood could be used as a template for recreating dinosaurs. It captured the imagination of an entire generation, and some version of that question, can we recover ancient DNA and use it to recreate extinct animals, has been a serious area of scientific inquiry ever since. The news on ancient DNA over the past few decades has been both more extraordinary and more sobering than either the optimists or the pessimists predicted. On the extraordinary side, ancient DNA recovery has made possible things that seemed like fantasy even 30 years ago. We have sequenced the genome of Neanderthals and Denisovans, our closest extinct human relatives. We have recovered usable genetic material from woolly mammoths frozen in Siberian permafrost. We have sequenced the genomes of extinct cave bears, cave lions, giant ground sloths. We have even recovered partial genetic material from specimens over 1 million years old, the oldest DNA sequence yet obtained. These are genuine scientific achievements of the first order, and the woolly mammoth case in particular has moved from pure research into something much more immediately practical. The company Colossal Biosciences, founded in 2021, has a stated goal of recreating a cold-adapted elephant capable of surviving in Arctic ecosystems, effectively a mammoth proxy, if not a true mammoth. Their approach uses CRISPR gene editing technology to introduce mammoth-specific genetic variants into the genome of the Asian elephant, the mammoth's closest living relative. The intention is not to recreate a perfect mammoth, but to recreate the functional adaptations, the dense fur, the subcutaneous fat layer, the cold-adapted blood hemoglobin that would allow an elephant to survive in the Siberian steppe. Whether this is good science, good conservation biology, or good ethics is a separate and genuinely complex question. But as a demonstration of how rapidly the technical capabilities have evolved, it is remarkable. In 1990, the year Jurassic Park was published, the very concept of targeted gene editing was in its earliest theoretical stages. Today, it is a commercially deployed technology that multiple companies are using as the foundation for genuine de-extinction programs. So, does this mean we can bring back dinosaurs? Here's where the sobering side enters. DNA is a molecule, and molecules, no matter how remarkable, are not immune to chemical degradation. They decay, they fragment, they oxidize. Under normal conditions, burial in soil, exposure to moisture, temperature changes, DNA becomes unrecoverable in tens of thousands of years. Under exceptionally favorable conditions, frozen permafrost, extreme aridity, unusual mineral environments, it can persist longer, but even under the very best circumstances we have documented, the oldest recoverable DNA is approximately 1.2 million years old. The last non-avian dinosaurs lived 66 million years ago. The gap between oldest recoverable DNA and dinosaur extinction is not a small one to bridge. It is not a matter of improving technology enough to read more fragmented sequences. It is a fundamental limit imposed by the chemistry of nucleotides, which simply cannot maintain their structural integrity across tens of millions of years regardless of preservation conditions. The amber preservation premise of Jurassic Park was examined directly by scientists in the years following the film's release. Several teams did find apparent DNA in amber-preserved insects, and the initial results generated enormous excitement. Subsequent work showed that the sequences were contamination, modern DNA from laboratory sources that had been mistakenly incorporated into the ancient amber samples. The amber simply does not preserve DNA over such timescales. The molecular damage is too complete, too comprehensive. So the direct approach, find dinosaur DNA, read it, recreate it, is not currently possible and may not become possible regardless of technological advancement. But there is another approach, and it is one that actual scientists, not science fiction writers, are actively pursuing. The birds. If birds are dinosaurs, and they are, then bird DNA carries within it the legacy of dinosaurian genetics. Not all of it. Not the parts that were unique to extinct lineages, to non-avian body plans, to features abandoned on the way to the modern bird. But a great deal of it. The fundamental gene families, the regulatory networks, the developmental pathways that build a vertebrate body, these are enormously conserved across evolutionary time. They can be found, in modified but recognizable form, in the genomes of modern birds. And there is a research program, pursued most publicly by the paleontologist Jack Horner and the developmental biologist Hans Larsen, that proposes to use this fact to create what they call a chickensaurus, or more formally, a reverse-engineered dinosaur-like phenotype produced from a modern bird through targeted modification of developmental gene pathways. The logic is as follows. A chicken embryo, during its development, briefly activates ancient developmental programs that were present in its dinosaurian ancestors. At a certain stage of development, chicken embryos have teeth, proper crocodilian-style teeth that are later suppressed by a regulatory gene network. At another stage, they have long clawed digits on their wings. At another, they have extended multi-bone tails. These ancestral features are not lost, they are suppressed. The genetic instructions for building them are still present in the bird genome, dormant but intact, like old blueprints in a filing cabinet that no one has opened in a long time. By identifying and modifying the regulatory genes that suppress these ancestral features, turning off the suppressor, allowing the ancestral program to run, researchers have produced chicken embryos with fully formed tooth-bearing snouts, embryos with elongated, more dinosaur-like tails. The research is ongoing, carefully controlled, and produced from an entirely scientific motivation to understand developmental genetics. But the implication is remarkable. You don't need ancient DNA to get back to a dinosaur-like phenotype. You just need to read the ancient instructions that are still sitting in the modern bird genome waiting. This approach will not produce a Tyrannosaurus rex. The genetic distance between a modern chicken and T-Rex is too great, the specific modifications too numerous and complex, to allow for anything like a full reconstruction of a non-avian dinosaur through this route. What it will produce, what, in some preliminary experiments, it already has produced, are creatures that look less like modern birds and more like their Mesozoic ancestors, creatures that serve as living windows into developmental biology, into evolutionary mechanisms, into the deep time encoded in every living genome. And there is something in that, in the fact that the dinosaurian past is not actually erased from biology, but merely written over, hidden behind regulatory layers that a skilled geneticist can in principle learn to turn on and off, that I find deeply, quietly, wonderful. The past is not gone. It is present in the genome of every bird that sings outside your window. It is there in the temporary tooth buds of a chicken embryo, in the transient clawed fingers of a developing sparrow wing. The Mesozoic era did not end. It went underground. It hid in the nucleus of every living cell in every bird alive today. And the science that's learning to read it, learning to trace that hidden inheritance, is doing something that, if you think about it in the right light, is genuinely analogous to archaeology, digging down through layers of time to find what lies beneath. Finding in this case, not bones but instructions, not fossils but living code. There are dinosaurs in our DNA, in the DNA of our chickens and our sparrows and our hawks and our crows. They never left. They're just written very small. Let us go deeper, literally deeper. The ocean covers approximately 71% of the Earth's surface. It has an average depth of roughly 3,700 meters. Its deepest point, the Challenger Deep in the Mariana Trench, plunges nearly 11 kilometers below sea level. And yet, despite these statistics being well known, their implications for our understanding of what might live in the ocean are rarely fully appreciated. The deep ocean is, in practical terms less explored than the surface of Mars. We have mapped the Martian surface with resolution of better than 1 meter per pixel over significant portions of the planet. We have driven rovers across its soil, analysed its rocks, drilled into its regolith. We have a far more detailed knowledge of Martian topography than we do of the ocean floor. The deep sea floor has been surveyed to high resolution, over perhaps 5 to 15% of its total area. The rest is known only in broad strokes, depth contours, general acoustic profiles, the occasional deep-sea camera deployment. The actual biology of most of the ocean floor is essentially unknown, and the deep ocean is not an empty place. It is not a desert. It is an ecosystem of extraordinary complexity and diversity, operating on energy sources, hydrothermal vents, chemical gradients, the slow rain of organic material from above, quite different from the sunlight-dependent systems we know at the surface. The discoveries of recent decades have transformed our picture of deep-sea life from sparse and simple to complex, strange, and still largely uncatalogued. Hydrothermal vent communities, first discovered only in 1977, support entire food webs based on chemosynthesis rather than photosynthesis, bacteria that extract energy from chemical reactions involving hydrogen sulfide rather than from sunlight. These communities were completely unknown to science before the late 1970s. Every deep-sea expedition returns with new species, not occasionally, routinely. The Census of Marine Life, a 10-year international research program that concluded in 2010, estimated that somewhere between 500,000 and 10 million species of marine organisms remain undescribed. The range of that estimate is itself instructive. We are not even sure of the order of magnitude of our own ignorance. Large unknown animals in the deep ocean are not merely hypothetically possible. They are, on current evidence, genuinely likely. We know the giant squid exist because of the evidence: tentacles in the stomachs of sperm whales, occasional bodies, and eventually, in 2004, the first video footage. Before that footage, the giant squid was in the uncomfortable position of being documented by physical remains but never observed alive, officially known to science but effectively invisible. The colossal squid, even larger than the giant squid, potentially reaching 9 meters in length and weighing up to 750 kilograms, was known only from beaks found in whale stomachs until 1981, when a partial juvenile was caught by fishing boats. A complete adult female was finally captured in 2007. Before 1981, the colossal squid was scientifically acknowledged, but had never been observed as a living animal. Think about that. The largest invertebrate known to exist on Earth was, until less than 50 years ago, known only from secondary evidence. The animal itself remained invisible. Now. Are there surviving Mesozoic marine reptiles in the deep ocean? The popular imagination has long toyed with this idea. The plesiosaur, the long-necked marine reptile that dominated Mesozoic oceans, has been proposed as a possible identity for sea monster sightings from Loch Ness to the Pacific Ocean for well over a century. The scientific case against this is considerable. Plesiosaurs were air breathers, they had no gills, and breathed air as we do. Large air-breathing animals are difficult to conceal even in remote ocean locations, because they must surface regularly. A surviving population of plesiosaurs large enough to sustain itself over 66 million years would need to be substantial, and would, in that time, have been encountered, collected, photographed, or stranded on beaches often enough to leave unambiguous evidence. The absence of that evidence is significant. Not conclusive, the ocean is very large, and our monitoring of it is incomplete but significant. The mosasaurs, large, highly derived lizards that dominated the late Cretaceous seas as top marine predators, are an even more compelling subject for speculation, because their closest living relatives, the monitor lizards and the varanids, are among the most successful large reptile lineages alive today. Mosasaurs were not dinosaurs. They were lizards, highly specialized, highly aquatic lizards, with 4 flipper-like limbs, streamlined bodies, and a second set of teeth on the palate for gripping prey. The largest, like Mosasaurus itself, reached lengths of 15 to 17 meters. They went extinct at the end of the Cretaceous, along with the non-avian dinosaurs. But the Varanid lineage, the monitors and their relatives, survived, and in the tens of millions of years since, monitor lizards have repeatedly demonstrated a tendency toward large size in appropriate ecological contexts. Komodo dragons, The largest living lizards, at up to 3 meters and 70 kilograms, are actually small compared to the extinct Megalania, an Australian monitor lizard of the Pleistocene that reached lengths of 5 to 7 meters and may have persisted until as recently as 40,000 years ago. Megalania may have been encountered by the first Aboriginal Australians. Legends of large reptilian creatures in Australian indigenous traditions have been connected tentatively and carefully with the possibility of actual Megalania encounters. A 7-meter monitor lizard would have been a formidable and memorable presence in any ecosystem. But Megalania is not what keeps deep ocean researchers thoughtful on quiet nights. What keeps them thoughtful is the consistent, stubborn thread of evidence suggesting that very large, poorly described animals are present in oceanic environments that we have not systematically surveyed. Oarfish, the longest bony fish known, reaching lengths of up to 11 meters, were dismissed as sea serpent fantasies by many naturalists until specimens began washing ashore with regularity in the 20th century. Their silvery ribbon-like bodies seen at the surface could plausibly account for some sea serpent accounts. But not all of them, and some of the accounts, the ones describing large serpentine animals with visible vertical undulation, moving quickly at the surface in ways that do not match any known large marine animal, remain genuinely unresolved. The possibility that the deep ocean contains large, unfamiliar animals is not cryptozoological fantasy. It is a straightforward extrapolation from the known facts of ocean biology. The deep sea is an unexplored frontier. It has already produced surprises. It will almost certainly produce more. Whether any of those surprises will prove to be descendants of Mesozoic lineages, whether the Cretaceous Sea will prove to have been not entirely erased but merely relocated to depths we haven't yet reached, is a question that current evidence cannot answer, but it can be asked. And in the asking, there is something genuinely thrilling. Let me tell you about a specific expedition. In 2004, researchers from the National Oceanic and Atmospheric Administration deployed camera arrays in deep water off the coast of the Pacific Northwest. The purpose was ecological survey, documenting the fauna of a deep-sea canyon at depths between 1,500 and 3,000 meters. What they found was, by all accounts, a healthy and diverse ecosystem of the expected deep-sea type: Pacific hagfish, rat-tail fish, numerous species of invertebrates. Standard results for that depth and region. But in a small number of frames from cameras deployed at the lower depth range, the analysis team found a sequence of images showing a large elongated shape moving through the water column at speed. The shape was present in 14 frames before moving out of camera range. It was too large to be any known fish species documented in that region at that depth. It was, by pixel analysis of the camera field of view, at least 5 to 6 meters in length. The NOAA team noted the images in their report and listed the organism as unidentified. They did not speculate about its nature. They did not claim anything unusual. They simply recorded what the cameras had captured and acknowledged that it was not something they could identify. That note, in a technical government survey report filed quietly and without fanfare, sits in a database somewhere. There is something about that I find both haunting and hopeful in equal measure. Not because it proves anything, it doesn't. The images were not high resolution enough to determine morphology, and there are several large known species, certain sharks, sleeper sharks specifically, that could potentially explain them, though none is a perfect fit for the location and depth. But because it represents what genuine science actually looks like, not dramatic announcements, not confirmed discoveries, the quiet accumulation of observations that don't quite fit the existing inventory, the patient logging of anomalies, the acknowledgement that the catalogue is incomplete, the ocean is still writing itself, and we are still learning to read it. Here is a question I find endlessly fascinating, even as I hold it carefully. Did humans ever see dinosaurs? Not through fossil study, not through scientific reconstruction. Did any human being, living in prehistory, actually encounter a living animal that descended from the non-avian lineages? An animal large and strange enough to be recorded in story, in art, in the accumulated oral traditions that humanity carries like a distributed library across tens of thousands of years? The most intellectually honest answer is, we don't know. But the question is more interesting than it might initially appear. Let me work through the layers. First, the timeline. Non-avian dinosaurs went extinct 66 million years ago. The genus Homo, our genus, appeared roughly 3 million years ago. modern Homo sapiens emerged perhaps 300,000 years ago. There is an enormous gulf between the extinction of the non-avian dinosaurs and the first appearance of any human being. A gulf so vast that direct encounter seems, on its face, impossible. But the fossil record is not a complete inventory of all animals that ever lived. It is a heavily biased sample, biased toward creatures that lived in depositional environments, that had hard bones, that were covered by sediment quickly after death, and that happened to have their remains discovered by the small subset of the human species that has been systematically looking for them over the past 2 centuries. The last formal record of many lineages in the fossil record does not necessarily represent the actual date of extinction. It represents the date of the last preserved fossil we have found. For common animals in rich fossil environments, these 2 dates may be close. For rare animals in poor preservation environments, they might be separated by millions of years. This is called the senior-lips effect in paleontology, the observation that the apparent timing of extinctions in the fossil record consistently underestimates how long animals actually persisted, simply because rare animals leave rare fossils. There are documented cases, not hypothetical, but documented, of animals surviving millions of years beyond their last known fossil record. The coelacanth is the most dramatic example, persisting 65 million years beyond what we thought was its extinction date. But there are others. The Monito del Monte, a small marsupial from South America, represents a lineage whose fossil record ended roughly 45 million years ago in South America, and yet is alive today in Chilean and Argentine forests. So, the question of whether some Mesozoic survivors persisted into hominid-era history, leaving fossil records that have not yet been found, this is not a frivolous question. The absence of evidence is not evidence of absence, particularly in geological time, now. There is another, more evocative possibility that some researchers have explored. The fossil record itself may have been a source of mythology. Adrienne Mayer, a folklorist and historian of science at Stanford University, has written extensively about the relationship between fossil discoveries and ancient mythology. Her book, The First Fossil Hunters, examines classical Greek and Roman accounts of giants, monsters, and hybrid creatures, and traces many of them to specific fossil-bearing localities where ancient peoples would have encountered the bones of large extinct animals. The griffin, that distinctive hybrid of eagle and lion, depicted consistently across ancient Greek, Scythian, and Middle Eastern art, bears a remarkable resemblance to Protoceratops, a ceratopsian dinosaur whose fossils are abundant in the Gobi Desert. The Gobi was traversed by ancient trade routes, and Protoceratops fossils are often found in eroding deposits in a characteristic position, with their beaked skulls and 4-limbed bodies partially exposed. If you found such a fossil, knowing nothing of paleontology, the large beaked skull, the forelimb impression, the wing-like fossil bones might plausibly suggest an eagle-lion hybrid. Mayer argues that ancient peoples were not credulous fantasists inventing monsters from whole cloth. They were doing what any rational observer would do, trying to make sense of genuinely strange physical evidence, and the physical evidence of fossil bones encountered without any interpretive framework would be genuinely strange. The Cyclops of Greek mythology, the one-eyed giant of Odysseus's encounter, may have its origin in fossil elephant skulls. The nasal cavity of a dwarf elephant skull, placed at the centre of the face with the eye sockets on either side, presents to a non-specialist exactly the appearance of a single enormous central eye socket. Fossil dwarf elephant bones are found on Mediterranean islands, including Sicily, which in ancient tradition was Cyclops territory. The thunderbird of many North American indigenous traditions, a vast bird of supernatural power associated with storms and seen as an apex spiritual being, appears in traditions from the Pacific coast to the Great Plains, and may in some traditions carry echoes of encounters with large bird fossils. The thunder horse of Lakota tradition, whose bones were periodically unearthed from the Badlands of South Dakota, was eventually connected by paleontologists to the massive fossil mammals of the Badlands, but the tradition predates any Western scientific awareness of those fossils by centuries. These connections are not proof. They are possibilities, interpretations, resonances between ancient accounts and paleontological evidence. And Mayer is always careful to present them as such, as hypotheses that explain the geographic specificity and morphological detail of certain myths, rather than as established facts. but they point to something genuinely important. The relationship between humans and the deep past is not simply academic. It is not simply a matter of modern scientists digging up ancient bones. The physical evidence of ancient life has been present in the world, visibly present, for as long as humans have been walking the earth. And humans, being the pattern-seeking, story-creating beings we are, have always tried to make sense of it. The dragon. Almost every human culture has some version of the dragon. The Chinese dragon, the European dragon, the wyvern, the nuka, the Asian naga, the Mesoamerican quetzalcoatl, serpentine or reptilian, often large, often powerful, often ancient in quality. The convergence is remarkable and has been noted by anthropologists for over a century. The explanations vary. Some researchers suggest the dragon represents a kind of composite predator archetype, assembled from the most threatening elements of real animals, the constriction of snakes, the claws of raptors, the size of large reptiles. An evolutionary psychology hypothesis. The dragon is what your brain constructs when it tries to imagine the worst possible predator. Others, like the paleontologist Paul Sereno and various folklore researchers, have noted geographic correlations between dragon legends and fossil-bearing localities. Chinese dragon traditions, which are the oldest and most elaborate with written records stretching back over 3,000 years, are concentrated in regions of China where large dinosaur and marine reptile fossils are abundant and often surface naturally through erosion. In ancient China, these fossils were recognized as dragon bones and were used as medicine. Chinese apothecaries have been grinding down dinosaur fossils and selling them as medicinal preparations for at least 2,000 years. The material is well documented in Chinese medical texts. It represents, by the way, a paleontological tragedy, the systematic destruction of fossil material, whose scientific value was unknowable at the time. But the point is that these fossils were present. They were found, they were interpreted, and they were woven into one of the most persistent and globally distributed mythological traditions in human history. Did ancient Chinese peoples simply find dinosaur bones and imagine dragons? Probably in large part, yes, but the legend is older than the medical practice. It predates the documented bone-collecting tradition, which means the question of whether the dragon tradition has roots in something other than, or older than, fossil discovery alone remains genuinely open. I am not suggesting that people saw living dinosaurs. I am suggesting that the deep past has always been present in the human world, in ways we are still learning to understand. That the relationship between living humans and the ancient world they walk on, the fossilized world, the world of bones in stone and forms in rock, is not something that began with modern paleontology. It is as old as curiosity itself. And in that long continuity, in the story of people finding strange bones in eroding hillsides and asking what they were, and weaving those questions into the stories they told around fires on dark nights, there is something that connects us across all of recorded time to the same fundamental human impulse that drives paleontologists and biologists today. The impulse to know, to understand, to locate ourselves in a larger story. The dinosaurs have always been part of our story, even when we did not have the words to name them correctly. I want to spend a little more time with the birds, because I think the intelligence angle is the most astonishing part of the story, and it does not get the attention it deserves. When people think about birds and intelligence, they often think of parrots, or perhaps the impressive but somewhat circus-like demonstrations of Alex the African grey parrot who, under the training of the animal cognition researcher Irene Pepperberg, demonstrated the ability to categorize objects by color, shape, and material, to use the concept of zero, and to make genuinely novel requests in spoken English. Alex died in 2007. His last words to Pepperberg, on the evening before he was found dead, words he had said many times before as a routine parting, were, "You be good, see you tomorrow, I love you." Whether I love you, in the mouth of a grey parrot, represents anything we would recognize as the experience of love is a genuinely difficult philosophical question. But the behavior itself, the routine, the ritual, the consistent exchange at parting, represents something about social bonds, about recognition, about the management of relationships across time. These are not simple things. These are cognitively demanding things, and they emerge from a brain the size of a walnut, in a lineage that diverged from ours more than 300 million years ago. But parrots, for all their extraordinary capabilities, are not the most impressive cognitive story in avian science. That title probably belongs to the corvids, the crows and ravens and jays and their relatives, a family so cognitively advanced that researchers have coined the phrase feathered apes to describe them. New Caledonian crows manufacture tools. Not find tools and use them. Manufacture them. They strip twigs to precise specifications, sometimes adding hooks by selecting forked branches and shaping them to create retrieval tools for extracting insects from holes. They have been observed manufacturing compound tools, combining multiple elements to make a tool no single element could have served. In laboratory conditions, they have solved multi-step problems requiring planning, problems that involve using one tool to retrieve another tool, which is then used to retrieve food, requiring the animal to hold the whole sequence in mind before beginning. The planning aspect is crucial, because planning requires a mental model of the future. An animal that plans is not simply responding to current stimuli, it is running simulations in its mind. It is imagining a sequence of events that has not yet occurred, and choosing actions in the present based on that imagined future. Ravens, meanwhile, engage in what cognitive researchers describe as tactical deception. In studies by Bernd Heinrich and others, ravens have been observed actively misleading competitors about the locations of cached food, performing deceptive moves, approaching empty locations with apparent purpose when competitors are watching, and then recovering real caches when the competitor's attention has shifted. This requires the raven to model what the competitor is thinking, to have a theory of mind in the technical sense, and to deliberately create a false belief in another individual's mind. Theory of mind was for decades considered a uniquely human cognitive capacity. Then it was found in great apes, then in dolphins, then in elephants, now in a modified but recognizable form in ravens. Each time the scientific community found it difficult to accept. Each time the evidence accumulated until acceptance became unavoidable. Scrub jays, a corvid species of the North American West, have been shown to remember not just what they cached, where they cached it, and when they cached it, but to account for the perishability of different food types and to recache items accordingly. If they cached a perishable food item in a location that has since been observed by a competitor, they will recache it in a new location, but only if the observer was a competent thief. They modulate their behavior based on the specific identity and demonstrated behavior of individual competitors. That is social intelligence, of a very high order. And here is what I want you to sit with. These cognitive capabilities did not arise de novo in birds. They did not appear from nowhere in some avian ancestor. They arise from the same fundamental neural substrate, modified, elaborated, refined over millions of years of selection, that the small theropod dinosaurs were already beginning to develop. The troodon, which we mentioned earlier, the late Cretaceous theropod with an encephalization quotient higher than most living reptiles, was not a bird. But it shared a common ancestor with birds. Its neural architecture, already trending toward increased complexity, was part of the same evolutionary trajectory that eventually produced the raven and the grey parrot. When we understand bird intelligence, we are understanding something about dinosaurian intelligence. We are getting a window, imperfect, filtered through 66 million years of further evolution, but real, into what the small theropods were capable of, into what intelligence might have looked like in the Mesozoic, and that, I find, changes the texture of the Cretaceous in my mind, makes it feel less like a world of thundering giants, and more like a world of alert, watching, thinking creatures, navigating complex social environments, making decisions, learning, adapting. The birds know things that we are only beginning to learn how to ask about. Let us stay with the birds for a moment longer and explore something even more scientifically astonishing, the phenomenon of magnetic navigation. Many species of migratory birds navigate using the Earth's magnetic field. This has been known for decades. What was not known, until relatively recently, is how they do it. The answer, when it came, was stranger than anyone had predicted. Many migratory birds appear to navigate using a quantum mechanical effect in specialized light-sensitive molecules in their eyes. Cryptochrome proteins in the avian retina are thought to produce quantum-entangled electron pairs when struck by photons, and these entangled pairs are sensitive to the magnetic field in ways that, depending on the strength and direction of the field, cause subtle differences in the bird's visual experience. The bird may literally see the magnetic field as a visual overlay on its normal vision. a continuous pattern of light and shadow that encodes direction and intensity information. Quantum mechanics, in an eye, in a bird. The phenomenon, called the radical pair mechanism, has been demonstrated in vitro, and behavioural studies are increasingly supportive of its role in actual bird navigation. If it is confirmed as the primary mechanism, and the evidence is growing, then migratory birds are the only known organisms to use quantum mechanics as a primary sensory tool. They are biological quantum sensors, built and refined over hundreds of millions of years of evolution, using physics that we, as a species, only formally described in the 20th century. The bird on your windowsill, the pigeon, the sparrow, the robin, is carrying in the specialized proteins of its retina, a technology that our most advanced physicists are still struggling to replicate artificially. A technology that was present in some form long before our species existed, long before mammals diversified, perhaps in the ancestral form, in the proto-magnetic sensitivity of ancient vertebrate nervous systems, long before the first dinosaurs walked the Earth. Life has been doing quantum mechanics for longer than we have known quantum mechanics exists. I find that genuinely staggering, and I find it deeply appropriate, the most ordinary creature of the everyday world turning out to be, on closer inspection, a vessel of wonders so deep they touch the foundations of physics itself. That is the birds. That is the most direct survivors of the dinosaurian lineage, carrying forward into our present world the intelligence, the social complexity, the biological ingenuity that was being shaped in the Mesozoic forests long before the first hominid stood upright on an African savanna. They are here, they are watching us, and they are, in many important ways, far more extraordinary than we have tended to give them credit for. I want to tell you more about what survival looks like across geological time. We tend to dramatize survival. We tend to think of it as something active, fleeing the catastrophe, fighting through the dark years, emerging triumphant into the new world. And for some lineages, something like that narrative may apply. The early bird lineages, diversifying rapidly in the Paleocene, filling the niches vacated by the mass extinction, growing large and strange and numerous, that is a story with some of the qualities of a recovery epic. But there is another kind of survival that is, if anything, more mysterious. The survival of the apparently unchanged. The crocodilian story deserves more space than we have given it. When the Chicxulub impactor struck, the global ocean temperature rose dramatically. The immediate aftermath included massive boiling of the ocean surface layers in certain regions, acid rain that turned the upper ocean acidic, and a collapse of the food chains that had sustained the marine ecosystems of the late Cretaceous. Mosasaurs, the huge, fully aquatic marine lizards, went extinct. Marine turtles were severely reduced. The ichthyosaurs had already gone extinct earlier in the Cretaceous, and the plesiosaurs, large and air-breathing and dependent on a food chain that collapsed, went with the event. But crocodilians, freshwater and estuarine, feeding on fish and small prey in the murky river systems, made it through. How exactly? The current leading hypothesis involves the detritus food web. While the photosynthesis-based food web collapsed, plants died, plant eaters died, the predators of plant eaters died. The detritus-based food web was more resilient. Organic material from dying vegetation fell into river systems. Aquatic insects, scavengers, and detritivores could survive on this material. Fish that fed on insects and organic detritus survived. Crocodilians that fed on fish and scavenged carcasses survived. It was an ugly, diminished, impoverished world. But it was a world with enough energy flowing through it to sustain the metabolic needs of a low-metabolism, opportunistic predator that could eat infrequently and reduce its activity during the worst periods. The crocodilians did not merely hide in the water and wait. They reduced, they slowed, they became, for a time, as close to metabolically inert as a living vertebrate can become. And in doing so, they lasted long enough for the world to recover around them. And then, when the forest grew back and the rivers filled again with fish and the prey, animals returned to the banks. The crocodilians were already there, waiting, as they had always waited, as they have always been particularly good at waiting. There is something I find deeply impressive about this quality of the crocodilians. Not the violence, though the attack speed of a large crocodile is remarkable, but the patience, the absolute geological patience. A large Nile crocodile lying in the sun on an African riverbank may spend 20 to 22 hours each day apparently doing nothing, moving as little as possible, conserving energy, waiting. And in that waiting, there is an efficiency so radical that it borders on invisibility. The crocodile is essentially absent from the energetic accounting of the ecosystem for those hours. It is there, but it is, metabolically speaking, barely present. And then the wildebeest come to the river to cross, and the crocodile is entirely present. This feast and fast strategy, consuming enormous prey items infrequently, rather than small prey items constantly, is what allows crocodilians to achieve their extraordinary size on relatively sparse caloric income. A large crocodile can survive physiologically on as few as 4 to 5 large prey items per year. This is not a limitation. It is an enormous competitive advantage in a world where prey is unpredictable, where seasons of plenty alternate with seasons of scarcity, where catastrophes, floods, droughts, the occasional mass extinction event, interrupt food availability for years or decades at a time. The crocodile is built for the long game, and in the long game it has no peers among living vertebrates. I want to say something about the tuatara that I find particularly moving as we close this section. The tuatara is, in scientific terms, a relict species, the last survivor of a once diverse lineage. It is what the fossil record would call a ghost lineage, a trace of something that was once widespread and varied, now reduced to a single species in a single, restricted location. There were, in the Mesozoic, hundreds of species of rhynchocephalians. They occupied niches across the globe. They were lizard-like and crocodile-like, and some that were, quite unlike anything living today, they were for much of the Mesozoic a successful and diverse group. Something, the radiation of lizards and snakes perhaps, with their more flexible metabolic strategies and reproductive methods, reduced them, pushed them into smaller and smaller ecological spaces. Eventually, except in the isolation of New Zealand, they vanished. The tuatara survived in New Zealand because New Zealand was, until roughly 1,000 years ago, free of terrestrial mammalian predators. Birds and reptiles had the island to themselves. There was no competition for the ecological space that tuatara occupied. Slow-growing, long-lived, patient, nocturnal, subsisting on invertebrates and occasional small vertebrates. Then humans arrived, and with humans, rats and eventually dogs and cats and weasels, and all the other accidental passengers of human expansion. The rats alone were devastating, eating tuatara eggs with enthusiasm, because the eggs were buried in soft soil and undefended against a predator that the tuatara's 240 million year evolutionary history had given it no preparation for. Tuatara nearly went extinct. By the mid-20th century, they had been eliminated from the main islands of New Zealand and survived only on small offshore islands that the rats had not yet colonized. Conservation intervention, intensive predator control, careful management of the remaining populations, and eventually predator-free mainland sanctuaries has allowed tuatara numbers to recover. There are now estimated to be over 100,000 tuatara, a number that would have seemed impossibly optimistic 100 years ago. The tuatara survived the Chicxulub impact. It survived the Paleogene and the Neogene and the Pleistocene and the great climate cycles of the Ice Ages. It survived, in compressed and reduced form, everything the world threw at it for 240 million years. It almost did not survive us. I find that a sobering thought. The most ancient surviving vertebrate lineage on Earth, the last of its kind, the holder of 240 million years of living inheritance, nearly destroyed in less than 1,000 years of casual habitat degradation and invasive species introduction. And I find it hopeful too that we noticed, that enough people cared enough to act, that the tuatara is now more numerous than it was 50 years ago, and growing. We can break things. We can also sometimes fix them, or at least stop breaking them. That matters. It matters enormously. Let me return to the Congo Basin and spend more time there, because the stories that come from that region deserve fuller treatment. The Mokele Mbembe is the most famous, but it is not the only anomalous animal reported from Central and West Africa. There is also the Amela Ntuka, reported from the border regions of Congo and Cameroon, described as a large, semi-aquatic, hornless animal with a single horn on its snout and the body of a hippopotamus-sized creature with a massive, heavy tail. It is described as extremely aggressive, attacking and killing elephants and hippopotamuses. The description has led some researchers to compare it to the ceratopsian dinosaurs, the horned dinosaurs, though the single nasal horn and semi-aquatic habits do not match any known ceratopsian particularly well. Others have suggested an undescribed large rhinoceros, or a surviving population of some other known African megafauna. No physical evidence has been collected. There is also the Nguma monine, described as a large, purely aquatic serpentine animal, and the mbielu, which locals describe as a large animal with plates growing from its back, a description that has drawn immediate comparisons to stegosaurs, though the animal is described as aquatic, which no known stegosaur was. I want to be careful here. The temptation, when you read these descriptions, is to map them onto known dinosaur types, the Mokele mbembe as a sauropod, the Amelantuca as a ceratopsian, the mbielu as a stegosaur, and to construct a narrative in which the Congo Basin harbours a relic Mesozoic ecosystem. That narrative is very appealing. It has the structure of a satisfying mystery story. But the honest scientific assessment is that these individual accounts, while they share some consistent elements within each reported type, vary enough in detail that firm conclusions are impossible. The Congo Basin supports a known fauna of extraordinary richness, and several large, poorly known species, particularly large semi-aquatic reptiles, are present. There are African forest elephants and forest buffalo, and giant ground pangolins, and a dozen other large mammals that Western science described formally only within the last century. There is no particular reason to invoke Mesozoic survivorship when known biology could account for many or most of the accounts. But, in 1980, an expedition led by Roy McCall, a biologist from the University of Chicago, spent several weeks in the Likuala region of the Republic of Congo, specifically looking for the Mokele mbembe. McCall was a careful scientist, skeptical of sensational claims, equipped with a thorough knowledge of the region's known fauna. He found no Mokele mbembe. He collected extensive testimony from local people, including what he believed were consistent descriptions of an animal unlike any known African species. He found an area of disturbed vegetation and a possible travel path that he could not account for with known fauna. And he returned, by his own account, more uncertain than he had been when he arrived. Uncertain is not the same as convinced. McCall remained cautious in his published conclusions. But the fact that a careful, skeptical scientist with extensive field experience came back from the Congo saying, "I do not know," is itself interesting. It suggests that the local accounts contained something, some consistent element, some specific quality that impressed a sophisticated observer as worthy of continued attention. I don't know what the Mokele mbembe is, if it is anything at all. But I know that the Congo Basin is not fully known. I know that large animals have been formally described from that region within living memory. I know that the local people who report this animal are not, by and large, people with any incentive to maintain a false tradition about a non-existent creature. They are people for whom accurate knowledge of the environment is practically important. Knowledge of what is in the water and what is dangerous and what is safe is not academic for communities that live along these rivers, and I know that the honest scientific position, here as elsewhere, is not "this is impossible," but "this is unconfirmed and we should continue looking." The looking matters. Even if what you find is the absence of evidence, that absence is information. And if, one day, someone comes back from the Likuala swamps with something that changes the picture entirely, the world will be a stranger and more magnificent place than it already is, which, as I have said before, is a prospect I find not frightening, but wonderful. Let us go deeper into the thought experiment of the surviving dinosaurs, because I think there are dimensions to it that we have not fully explored. One of the most interesting and most scientifically grounded aspects of the surviving dinosaur hypothesis concerns the ecology of the continents. In the late Cretaceous, the continents were not in their current positions. North and South America were separated. The isthmus connecting them would not form until roughly 3 million years ago. India was an island, drifting northward toward its eventual collision with Asia. Antarctica, while in approximately its current position, was considerably warmer and forested. Australia was partially connected to Antarctica and moving steadily northward. This geographic fragmentation would have had profound consequences for dinosaurian evolution over subsequent millions of years. Just as the separation of South America allowed the terror birds to evolve in isolation from the placental predators of the north, the continuing geographic separation of the continents in our hypothetical surviving dinosaur world would have produced parallel divergent evolutionary experiments on each landmass. The North American theropods, tyrannosaurs, dromaeosaurs, or nithomemosaurs would have continued evolving in the context of their own herbivore communities, with hadrosaurs and ceratopsians as the primary prey base. The tyrannosaur lineage might have diverged into specialized forms for different prey types, perhaps smaller, faster tyrannosaurs adapted for ceratopsian hunting, very different in body plan from the bone-crushing generalist we see in the late Cretaceous record. South America, which in the Cretaceous had its own distinctive dinosaurian fauna, the enormous titanosaur sauropods, and the abelisaurid theropods that dominated its apex, predator niche, would have evolved in geographic isolation for tens of millions of years longer than it did in our world. Abelisaurids are a fascinating lineage, shorter-armed than tyrannosaurs, with heavily reinforced skulls suggesting they used their heads as battering rams in prey capture, and with elaborate horn-like ornamentation on the skull roof in some species. Given millions more years of evolution, the abelisaurid lineage might have become something extraordinary, more cognitively complex perhaps, or more socially sophisticated, or larger, or more specialized. Africa, in the Cretaceous, had its own unique fauna. The spinosaurs, the large semi-aquatic fish-eating predators, were particularly diverse and successful in North Africa. The Spinosaur lineage, given more time, might have moved more completely into the aquatic niche, producing something genuinely crocodilian in aspect though built on a theropod body plan. Large, long-snouted, primarily aquatic spinosaurs coexisting. With the actual crocodilians in African river systems, the competitive dynamics of that ecosystem would have been extraordinary. India, isolated on its journey across the Tethys Sea, had a dinosaurian fauna that we're only beginning to understand from the fossil record. Several unique titanosaur lineages and interesting small theropod groups inhabited the subcontinent during its island phase. In a world where the asteroid missed, the Indian subcontinent's collision with Asia, a process that created the Himalayas in our world, and that would have occurred in the alternate world as well, would have been an event of enormous biological consequence. Two previously isolated faunas suddenly brought into contact, with the mountain ranges that resulted providing new high-altitude ecological niches for dinosaurian adaptation. The high-altitude dinosaur is something I find particularly interesting to think about. In our world, the Himalayas and other high mountain ranges created new ecological niches for mammals, the yak, the snow leopard, the Tibetan antelope, all adapted to the specific challenges of high altitude. In a world where dinosaurs were still the dominant vertebrate megafauna, those mountain niches would have been filled by dinosaurs, cold-adapted, thick-feathered theropods, perhaps even secondary gigantism in high-altitude environments, where a larger body mass helps retain heat. The polar dinosaurs are not hypothetical, by the way. In our world, there were dinosaurs living within the Antarctic Circle, and near the Arctic we have their fossils. Lialinnosaura and Muttaburrasaurus, from what is now southeastern Australia, which in the early Cretaceous was within the Antarctic Circle, Pachyrhinosaurus, and hadrosaurs from the north slope of Alaska. These animals were dealing with polar winters, months of continuous darkness, and must have had physiological and behavioural adaptations for this that we can only partially reconstruct. In a world where dinosaurs continued evolving for 66 million more years, polar dinosaur lineages would have had enormous time to optimize for cold environments, to develop the kind of metabolic flexibility that allows modern caribou or musk oxen to survive Arctic winters, to develop wool-like or down-like integument dense enough to function in temperatures well below zero. There is something arresting about imagining a world in which, instead of polar bears and musk oxen and wolverines, the Arctic ecosystems are occupied by large feathered theropods, their breath steaming in the cold air, their feathers fluffed against the wind, hunting the equally large and adapted herbivores of the high latitudes. That world did not happen, but it almost could have. And here is the thing that geology keeps reminding us. The universe does not care about almost. The asteroid arrived at the angle it arrived at and struck the geological formation it struck. And the rest, the emptying of the ecological stage, the rise of the mammals, the emergence of us, followed with the remorseless logic of physical law. But in the contemplation of what did not happen, there is something that illuminates what did. Because the fact that our particular world required a catastrophic clearing event to allow mammals to rise, the fact that we owe our existence to a disaster of incomprehensible scale, puts our existence in a light that is simultaneously humbling and, I think, extraordinary. We are in a sense the children of catastrophe, the inheritors of an emptied stage, the beneficiaries of a clearing that cost 3/4 of all life on Earth. That debt is worth holding. Not with guilt, which would be absurd. We were not there. We had no choice. We are simply the result of what happened. but with a kind of solemn awareness, a recognition that our presence here is not inevitable, that the universe did not plan for us, that we are contingent in a way that is both sobering and somehow wonderful. We are an unlikely outcome of an unlikely event on an unlikely planet in an unlikely corner of an unlikely galaxy. And yet here we are, thinking about dinosaurs in the dark. There is something in that worth appreciating. The idea that the genome is a kind of fossil, carrying the record of evolutionary history in its sequences, is one that has transformed biology over the last few decades. Let me go deeper into what that actually means, and what it reveals about the dinosaur connection. Every genome is palimpsest, a document written over and over again, with traces of older writing still visible beneath the newer text. When a genome is sequenced, what you're reading is not just the current instructions for building an organism. You're reading the accumulated record of every modification, every mutation, every duplication and deletion and inversion that has happened in that lineage since the beginning of life. Most of those modifications are silent. They sit in the non-coding regions of the genome, the vast stretches of DNA that do not code directly for proteins, and they accumulate at a relatively steady rate, like the growth rings of a tree, allowing geneticists to estimate when two lineages diverge from each other based on how different their accumulated mutations have become. This molecular clock, as it is called, has allowed geneticists to reconstruct the tree of life with extraordinary precision. And every time a new genome is sequenced, every time the full genetic text of a new species is read for the first time, it adds another data point to the picture of how all life on Earth is related. The chicken genome was fully sequenced in 2004. Its analysis was revelatory. For one thing, it confirmed with absolute molecular certainty the relationship between birds and other theropod dinosaurs. The genetic distance between a chicken and a crocodile, which, as we noted, represents the closest living non-avian relative of the dinosaurs, is less than the genetic distance between a chicken and a human. Birds and crocodiles are more closely related to each other than either is to us. More recently, the genomes of multiple bird species have been sequenced and compared, allowing geneticists to map the evolutionary relationships among all living bird families and to identify which genes have changed the most and which have been most conserved across the diversification from a common avian ancestor into the extraordinary diversity of modern birds. One of the most intriguing findings concerns the genes for teeth. Birds do not have teeth. No living bird species has teeth. The last toothed birds went extinct roughly 60 million years ago in the early Paleogene, as a series of mutations disabled the genetic pathway for tooth development in the ancestors of all living birds. But the genes are still there, deactivated, fragmented, but present. The chicken genome contains the remnants of the genes for enamel formation, the outer coating of teeth, and for dentin formation, the inner structure. These genes have been modified by mutations that prevent them from being expressed, but they have not been deleted. They sit in the chicken genome like old tools in a drawer, no longer used, not quite thrown away. This is why, when researchers managed to partially reactivate the ancestral tooth development pathway in chicken embryos, teeth actually grew. The instructions were still there. They just needed to be switched back on. What other ancestral features are sleeping in bird genomes, waiting to be woken up? The clawed wing fingers, the 3 digits of the bird's wing, which in ancestral dinosaurs were free, clawed, manipulative fingers, have been partially reactivated in embryo experiments as well. Modern bird embryos, at an early developmental stage, briefly develop digit structures that resemble the free-clawed fingers of their non-avian ancestors, before the regulatory program that fuses and modifies them into the modern wing structure takes over, the tail. Modern birds have a short fused tail structure, the pygostyle, that supports the tail feathers. But embryonic birds go through a stage with a much longer, multi-vertebrae tail before the developmental program shortens and fuses it. The ancestral long tail has not been deleted from the program. It is expressed briefly and then overridden. Every one of these transient developmental features is a window into the past. A brief moment in which the embryo recapitulates, imperfectly and incompletely, something of the body plan of its ancestors. An echo, in development, of deep evolutionary time. The field of evolutionary developmental biology, evo-devo as it is called, has transformed our understanding of how evolution actually works. Rather than building new organisms from scratch, evolution modifies existing developmental programs. It tweaks the timing of when certain genes switch on or off. It amplifies or suppresses existing processes. It repurposes structures that were present in ancestors for new functions. This is why, as Jack Horner has argued, creating a chickenosaurus, a chicken with certain ancestral dinosaurian features reactivated, is not science fiction. It is in principle a matter of identifying the regulatory genes responsible for suppressing specific ancestral features and modifying them. The underlying instructions have not gone anywhere. They are in the genome, waiting. Whether a chickenosaurus should be created is a different question, one involving ethics, practicality, public perception, and the question of what such a creature would actually tell us about dinosaurian biology that we could not learn more cleanly from other methods. Many paleontologists have pointed out that a chicken with reactivated teeth and a longer tail would not be a dinosaur in any scientifically meaningful sense. It would be a genetically modified chicken with some atavistic features, not representative of any extinct species. But the intellectual point stands regardless of the practical application. The dinosaurian genome is not extinct. It lives in modified and edited form in every bird alive today. Every morning, as bird embryos develop in eggs around the world, the ancient instructions are read, partially expressed, modified, and finally overwritten by the modern developmental program. The past is always briefly present in the becoming of the present. That, I think, is one of the most quietly extraordinary facts in all of biology. The Mesozoic is not in a museum. It is in a nest. I want to take you somewhere specific, somewhere that very few humans have ever gone. The Twilight Zone. Not the television series, though it was named, with appropriate atmosphere, for the same quality of dimness and uncertainty. The mesopelagic zone of the ocean, the layer between roughly 200 and 1,000 meters depth, is called the Twilight Zone because it receives just enough light from the surface to be barely dimly illuminated during the day, but not enough to support photosynthesis. It is a layer of permanent deep blue, lit only by the faint ghost of the sun filtering down from above. It is also one of the largest habitats on Earth and one of the least understood. The Twilight Zone contains more fish, by mass, than all the world's surface fisheries combined. This estimate, which comes from acoustic surveys of the layer, emerged only in the last few decades and was greeted with considerable surprise by oceanographers who had assumed the deep sea was relatively sparse. The Twilight Zone biomass is enormous. It supports vast numbers of small fish, squid, crustaceans and jellyfish that migrate upward toward the surface at night to feed and sink back into the dim zone during the day, performing the largest daily migration of biomass on Earth, twice every day, invisibly, in the depths. And into this migration, into the vast twilight biomass, swim predators from above. Sperm whales dive into the Twilight Zone and beyond to hunt giant squid. Swordfish and marlins extend their ranges into the upper Twilight Zone. Sharks of various species inhabit its permanent darkness. And at the lower boundary, at the transition into the true deep ocean, at depths where the pressure would kill an unprotected human in moments, live creatures that represent some of the most ancient body plans in existence. The frilled shark, a species that has barely changed since the Devonian period over 300 million years ago. It has 6 gill slits instead of the 5 that most sharks have, a relic of a more ancient configuration. Its teeth are tricuspid, 3-pointed, in a form found in sharks from the Devonian fossil record. Its body is elongated and eel-like, more reminiscent of an ancient proto-shark than of the torpedo-bodied modern sharks we are familiar with. The frilled shark is, in every formal sense, a living fossil. It was formally described only in 1884, and live specimens are still rarely observed. It dwells primarily in depths of between 400 and 1,500 meters, emerging occasionally into shallower water, where it has been accidentally caught by fishing boats or encountered by deep-sea cameras. When a frilled shark appeared in a Japanese marine park in 2007, caught by fishermen who released it into a holding tank before it died shortly after, it was described by observers as moving like a sea serpent. The eel-like body, the frilled gills, the unusual swimming motion produced by an undulating spine rather than a swept tail, all of it deeply unfamiliar, deeply ancient, seeming profoundly strange even to people who knew what fish looked like. If the frilled shark can have been present in Earth's oceans for over 300 million years, inhabiting the deep water, rarely surfacing, essentially invisible to human observation until the advent of deep-sea trawling in the 19th century, what else might be down there? The question is genuine, not rhetorical, genuine. We do not know what lives at the greatest, ocean depths. We have sampled those depths, but sampling is not surveying. A camera deployed for a few hours in a canyon floor covers a tiny fraction of the available area. A trawl net catches what happens to be in a particular water column at a particular moment. The rest, the vast majority of the volume and area of the deep ocean, remains unobserved. New species of shark are described every year. New species of fish. New species of invertebrates too numerous to count. In 2006, a species of large deep-sea shark, the ninja lantern shark, subsequently named Etmopterus benchley, was collected in the Pacific. It was not some tiny, obscure creature. It was a perfectly formed, intact, meticulously evolved shark, a metre-long bioluminescent entirely new to science. In 2019, 4 new species of sleeper shark were described from specimens collected in the deep Pacific and Indian Oceans. Sleeper sharks, which can grow to lengths of 7 meters or more, making them among the largest sharks in existence, had been thought to comprise a small number of well-known species. Instead, systematic genetic analysis revealed multiple previously undescribed species, including some of substantial size. Large animals, unknown, in the ocean, in the 21st century. The deep sea keeps its secrets, and I find myself thinking in the small hours about what those secrets might include, about the long serpentine shapes that appear occasionally in the stomachs of sperm whales, shapes from animals that the whale has eaten, but that cannot be identified from fragments, about the anomalous acoustic signatures recorded by deep-sea hydrophone arrays that do not match any known biological source, about the occasional deep-sea camera footage of shapes that move in ways that do not quite match anything in the catalogue. Most of these anomalies have explanations. Most of them will turn out to be known animals seen at unusual angles, or unusual behaviours of known species or artefacts of the recording equipment. That is the most likely outcome, but not all of them. And in the honest acknowledgement of that uncertainty, in the scientific habit of holding open, rather than prematurely closing, the question, there is something that feels, to me, like the proper attitude toward a world that has repeatedly shown us it is larger, stranger, and more varied than we thought. The deep ocean is dark, it is cold, it is under enormous pressure, it is very, very large, and it has been there, undisturbed in its deepest parts for hundreds of millions of years. Whatever is down there, whatever we know about and whatever we do not, has had all that time to become very good at what it does. Let me tell you about some of the scientists who transformed our understanding of dinosaurs, because the story of how we came to know what we know is as interesting as the knowledge itself. For most of the 20th century, the standard model of dinosaur biology was essentially inherited from Victorian natural history. Dinosaurs were cold-blooded, slow-moving, swamp-dwelling animals, overgrown reptiles, essentially. Their extinction was seen as almost inevitable, the final chapter of an evolutionary experiment that was already past its prime when the asteroid arrived. This view was wrong in almost every important way, and the process of correcting it was one of the most sustained and contentious revisions in the history of paleontology. John Ostrom was one of the first to begin the revision. In the 1960s and 1970s, Ostrom's work on Deinonychus, a large, highly agile dromaeosaur from the early Cretaceous of Montana, fundamentally changed the picture of small theropod dinosaurs. Deinonychus was not a lumbering reptile. It was built for speed and agility, long-legged, lightweight, with a sickle-shaped killing claw on each hind foot that clearly served as an active weapon, requiring the animal to balance on one leg while kicking with the other. This required balance. This required coordination. This required, Ostrom argued, a nervous system and a level of metabolic activity quite different from the traditional cold-blooded model. Ostrom also recognized the detailed anatomical similarities between Deinonychus and Archaeopteryx, and in a series of papers in the 1970s, made the formal argument that birds were direct theropod descendants, not merely related to dinosaurs, but literally descended from them within the Maniraptoran theropod lineage. This view, now universally accepted, was deeply controversial at the time and won acceptance only slowly, against significant resistance from ornithologists who were reluctant to accept that birds were, in the taxonomic sense, dinosaurs. Robert Bakker, Ostrom's student and one of the most influential and controversial paleontologists of his generation, took the warm blood hypothesis and ran with it, dramatically, provocatively, with the kind of confident iconoclasm that both accelerates scientific progress and antagonizes scientific colleagues. Bakker's 1975 paper and his subsequent popular book, The Dinosaur Heresies, argued forcefully for dinosaurian endothermy, warm-bloodedness, and for a view of dinosaurs as active, socially complex, behaviorally sophisticated animals much more like large birds and mammals than like modern reptiles. Bakker was right about some things and wrong about others. The picture of dinosaurian metabolism that has emerged from subsequent research is more nuanced than either the old cold blood model or Bakker's fully warm blood alternative. Many dinosaurs appear to have been mesotherms, operating at metabolic rates between those of modern ectotherms and endotherms, and possibly able to adjust their metabolic rates across a wider range than modern animals can. But the fundamental revolution that Bakker helped drive, the recognition of dinosaurs as dynamic, active, behaviorally complex animals, has proven durable. Jack Horner, whom we mentioned in the context of the Chickenosaurus project, made his most important early contributions through paleontological fieldwork in Montana. In 1978, he and his colleague Bob McKellar discovered a nesting colony of Maiasaura, a large hadrosaur, at a site now called Egg Mountain. This discovery was transformative. The Egg Mountain site contained not just eggs and hatchlings, but evidence that the hatchlings had been present in the nest for an extended period after hatching. Their bones showed wear from growth and movement. The nest bowl was filled with what appeared to be the remains of vegetation brought as food, and the juveniles showed no obvious escape behavior, suggesting they were attended by adults. Maiasaura, the name means good mother lizard, apparently practiced extended parental care. The young were not precocial, capable of fending for themselves immediately after hatching, but altricial, helpless, requiring parental investment. This was not the behavior of a cold-blooded reptile, it was the behavior of a bird or a mammal. It was the behavior of an animal for which individual offspring were costly investments, warranting protection and provision over an extended period. The implications rippled outward from that Montana site. If hadrosaurs practiced parental care, what other dinosaurs did? Were herds and flocks and colonial nesting behavior more common than had been assumed? Did the complex social behaviors that we associate primarily with warm-blooded vertebrates have a long history in the dinosaurian lineage? The answers, as more and more evidence has accumulated, increasingly point toward yes. Fossil nesting sites of various dinosaur species show evidence of colonial nesting, large numbers of nests in close proximity, in some cases laid out in what appears to be organized patterns, evidence of nest site fidelity, the same locations used year after year by returning adults. Evidence of egg incubation behavior, including large theropods apparently brooding their eggs in a manner exactly analogous to modern birds. An oviraptor, a small theropod long accused, on the basis of a misidentified specimen, of stealing eggs, was found in Mongolia, brooding a clutch of its own eggs in exactly the posture of a brooding bird. Arms spread, body over the nest, the eggs positioned to be covered and warmed by the brooding adult's body heat. Oviraptor, despite its name, egg thief, was a devoted parent. This kind of discovery, the steady accumulation of behavioral evidence, extracted from stone by patient and ingenious scientists, has transformed dinosaurs from museum pieces into something far more alive in the imagination. Something we can relate to. Something whose lives we can, to some degree, reconstruct and understand. They fought. They nested. They raised their young. They communicated. They navigated complex social environments. They migrated, some of them, across hundreds of kilometers, leaving their trackways pressed into ancient riverbeds that hardened and fossilized and waited 65 million years for us to find them. And in doing all of this, they were, in the deep grammar of behavior and biology, not so very different from us. Let me take you to a different kind of fossil. Not bone, not impression in stone, but something more intimate, more immediate, more startlingly preserved. Amber. Amber is fossilized tree resin, the sticky aromatic substance that certain trees produce in response to wounds or infection. In the Cretaceous forests, as in forests today, resin oozed from the bark of coniferous trees, and sometimes, very occasionally, things became trapped in that resin before it hardened. The things trapped in Cretaceous amber represent a direct sample of the Mesozoic world in a way that no other fossil type can match. Not the compressed remains of bone in rock, translated through millions of years of mineralization, but the actual bodies, intact, sometimes in extraordinary detail of creatures that lived and died in the Cretaceous forests, insects, spiders, feathers, dinosaur feathers, now preserved in 3 dimensions, their microscopic structures intact enough to determine their original colours through the analysis of melanosomes, flowers, pollen, fragments of bark and leaf, and occasionally remarkably more. In 2016, a team led by Li Dexing at the China University of Geosciences described a piece of Burmese amber from deposits approximately 99 million years old that contained the preserved tail of a small coelurosaur dinosaur, not a feather, not a fragment. A tail section about 4 centimeters long, with the feathers still attached in their original arrangement, and soft tissue preserved beneath the feathers, and what appears to be bone within the soft tissue, a 99-million-year-old dinosaur tail, preserved in amber, 3-dimensional, real. The feathers on this specimen, which the researchers nicknamed Eva, are preserved in extraordinary detail. They are complex feathers, not the simple filamentous proto-feathers of the earliest feathered dinosaurs, but fully developed, branched feathers with araceous and barbs. They are chestnut brown above, white below, based on melanosome analysis. This tiny coelurosaur had a patterned 2-tone tail. Eva was not the only such discovery. In the same amber deposits, Xing's team also found the wing of an enantiornithine bird, an extinct lineage of Cretaceous birds, preserved in such detail that individual flight feathers could be examined, the arrangement of primary and secondary feathers documented, the microstructure of the feather surface analysed. The wing looked, to modern eyes, remarkably modern, strikingly similar to the wing of a small perching bird today. It was 99 million years old. These amber specimens represent something remarkable, a direct, physical connection across deep time. When you look at photographs of Eva's tail, you're not looking at a reconstruction. You're not looking at an artist's interpretation of fragmentary evidence. You're looking at the actual remains of an actual animal that was alive and moving through a Cretaceous forest 99 million years ago. The amber archived it, held it, waited, and now we get to see. I find this profoundly moving. There is something about the intimacy of the amber specimens, the scale of them, the detail, the way they bring the Cretaceous down from the vast and abstract to the specific and immediate that the great fossil skeletons, for all their drama, do not quite achieve. A skeleton in a museum is impressive. It communicates size, structure, the engineering of biology. But an amber specimen is personal. It says, this creature was small. It had individual feathers. Its tail was this particular shape and these particular colours. It was specific. It was this animal, on this day, in this forest. And then the resin closed over it, and the forest grew on, and the continents moved, and the glaciers came and went, and the mammals rose and diversified, and the primates came down from the trees and learned to make fire and eventually to make electron microscopes. And now we have Eva. We have the actual tail of a dinosaur from a forest that existed before most of the modern mountain ranges, before most of the modern ocean floor, before most of the geography of the modern world. We have it. We can hold it up to the light and count the feather barbs. That, to me, is one of the most astonishing facts of our present moment. Not the space telescopes or the particle accelerators, remarkable as those are, the ability to hold in our hands a piece of the Cretaceous, to read the colours of its inhabitants' feathers from the chemistry of their melanosomes. We are in this century learning to read the past in ways that previous generations could not have imagined, and every reading teaches us that the past was more alive, more complex, more full of specific, vivid individuals than the abstract numbers of geological time suggest. The dinosaurs were not abstract. They were specific. They had colours. They had patterns. They had behaviours shaped by their individual circumstances. They had, in all probability, individual lives that mattered to them in whatever way lives can matter to a non-human creature. And they are still here. In the birds, yes, in the genomes. But also in the amber. Also in the stone. also in the ongoing project of science that, piece by piece, is bringing them back into focus. I want to explore something a little different here, the possibility that our relationship with dinosaurs is not purely intellectual, that it is also, in some deep and pre-rational sense, biological. Human beings are afraid of certain things with an intensity that seems out of proportion to their actual current threat. We're afraid of spiders and snakes at rates that far exceed the actual danger they pose in modern environments. We're afraid of heights and of open spaces and of deep water. We are not particularly afraid of cars, despite cars being far more likely to kill us than any of the things we instinctively fear. This pattern makes sense when you understand that the fear responses that evolution has built into our nervous systems were shaped not by the modern environment, but by the ancestral one. The African savanna, the forest, the open plain where our primate ancestors were genuine prey for genuine predators. And those predators, for the entire evolutionary history of our primate lineage, going back 60 million years and more, included large reptiles. Not dinosaurs specifically. Our primate ancestors evolved long after the non-avian dinosaurs went extinct. But large snakes, large monitor lizards, and large crocodilians have been predators of primates for the entire time our lineage has existed as primates. The terror of the serpent is genuinely ancient in our biology. The freeze response when something large and reptilian moves nearby is genuinely ancient. Some evolutionary psychologists have gone further, suggesting that the specific combination of features we find most terrifying in predators, large body, reptilian texture, sudden movement, the ability to strike without warning, may have created in the deep history of vertebrate prey animals a generalized large reptile fear response that predates our primate ancestors. That was present in some form in the small mammals of the Mesozoic era, who lived their entire lives in a world where large theropod dinosaurs were the apex terrestrial predators. This is speculative. Evolutionary psychology is a field with real scientific contributions, and also real overreach, and it is important to hold its more dramatic claims with appropriate caution. But there is something interesting in the observation that our most intense, most visceral fears tend to cluster around the same categories of threat that were most dangerous to our deep vertebrate ancestors, and that the dinosaurs, or rather the template of the large theropod predator, fits those categories with unsettling precision. The T-Rex of popular culture terrifies people in a way that goes beyond intellectual recognition of danger. It triggers something that feels pre-rational, something that recognizes, at a level below conscious thought, the shape and posture and quality of movement of a top predator. Perhaps that recognition is not surprising. Perhaps, in some dim way, it is the same recognition that kept our small mammalian ancestors alive in the shadow of the tyrannosaurs. A recognitional system built into our biology, shaped by selection, that says, this shape, this movement, this scale, this context, run. We no longer need to run from tyrannosaurs, but the recognition system remains. And when we see the skeleton of a large theropod in a museum, when we look at the skull of T-Rex with its metre of bone and its serrated teeth, and its forward-facing predatory eyes, something in us responds with an immediacy that goes beyond the academic, with something that feels like memory, though it cannot be personal memory, with something ancient and embodied and real. We are, in that moment, meeting something we have known for a very long time. Let me come back to the present, to the specific and immediate world of right now. It is early morning somewhere, the sky's lightening at the edges, and in the trees, in the hedges, in the eaves of buildings and the reeds of marshes and the high thermal columns above city parks, the birds are beginning. The dawn chorus. The daily assertion of territory and presence that birds have been making every morning since before the first human walked. Every species singing its specific song, coded in its genes, learned from its parents, shaped by selection for the qualities that most effectively communicate fitness and territory and readiness. The dawn chorus is not a modern invention. It is not a recent development. The species singing in your local trees have been singing similar songs in this same general context for millions of years. The ancestors of robins were singing in the early morning in Miocene forests 15 million years ago. The ancestors of sparrows were singing in the Eocene dawn 30 million years ago. The ancestors of all of them were singing in the Paleocene 50 million years ago, in the recovering forests of the post-impact world. This is not an interruption of the dinosaurian story. It is the continuation of it. When you hear the dawn chorus, really hear it, not as background noise, but as the thing it actually is, you're hearing 66 million years of unbroken continuity. You're hearing the descendants of the only dinosaurian lineage that made it through the worst day in the history of animal life. You're hearing proof that survival is possible, that catastrophe is not always ending, that the world on the other side of devastation can still be filled with song. There is something in that which I find, on certain mornings, almost unbearably beautiful. The crow on the telephone wire is a dinosaur. It is watching you with eyes that see, in 4 colour bands where you see only 3. Ultraviolet light is visible to birds, painting the world in colours we have no names for, no experience of. It is watching you with a brain that can hold a map of the territory it lives in, that can remember individual humans and their behavioural patterns, that can solve novel problems with tools. It is watching you from 66 million years of continuity, from a lineage that survived everything, and it does not especially care whether you appreciate any of this. Crows are not interested in your appreciation. But I think they are interesting. I think the whole story, the asteroid, the dark years, the survivors, the birds, the living fossils, the mysteries at the edge of the map, is interesting in a way that very few stories manage to be. It is interesting because it is true. It is interesting because it is ongoing. It is interesting because it involves us. We are not outside this story. We are in it. We are part of the continuation of the project that the dinosaurs began, the project of large, complex, behaviourally sophisticated vertebrate life on Earth. We inherited the ecological opportunities they vacated. We carry in our own genomes the same fundamental vertebrate development programs that build their bones and ours from the same ancient blueprints. We are their successors, and they are our predecessors, and the birds are both our neighbours and their descendants, and in the crow's black eye the whole improbable, magnificent 66 million year story looks back at us. The dinosaurs are still here, and so, in the most meaningful sense, are we. As you drift now towards sleep, let the story settle into you. Let the deep times spread out around you like a vast, dark ocean, and let yourself float on its surface. The Cretaceous below, the Paleogene, the long march of the Cenozoic. The brief, brilliant, improbable moment of us. And all around us, the birds, in the dark trees, on every wire, in every marsh and forest and city park and ocean cliff, carrying the inheritance of the Mesozoic forward, day by day, song by song, nest by nest, generation by generation. They were here before us, they will be here after us, and in the night when the world is quiet and everything is still and the stars are out, they are sleeping somewhere in the dark branches, dreaming perhaps whatever birds dream. 66 million years of survival, 66 million years of mornings. Sleep well. Where in the world are you watching from? Let us know in the comments, and do not forget to subscribe if you want to see more videos like this.